If you like the space and learn about its curiosities, subscribing to the channel. Thank you for your attention and enjoy the video. The life and death of stars. Stars have fascinated humanity for millennia, acting as celestial guides, sources of inspiration, and the ultimate symbols of mystery. But have you ever wondered what truly brings them to life? How does an object, born from the chaos of space, begin to shine so brightly that it dominates the night sky? The life of a star is not just a cosmic accident. It's a symphony of physical laws, a masterpiece of energy and transformation that starts deep within the vast molecular clouds scattered across the universe. When we look up at the stars, we are gazing back in time. The light we see from a star today might have begun its journey millions, even billions of years ago. These glowing orbs are not eternal. They are born, they age, and they die, leaving behind a legacy of cosmic ingredients that shape the universe itself. Understanding how stars live and die is to uncover the intricate story of the cosmos, from the smallest particles to the largest galactic structures. At the heart of stellar evolution lies the delicate interplay of two opposing forces, gravity and pressure. Gravity works tirelessly, pulling matter inward, while pressure, generated by nuclear reactions within a star's core, pushes outward. This tug-of-war determines the lifespan of a star and the dramatic way it will eventually meet its end. But the journey from the cold, dark void to a blazing sphere of light is far from simple. It begins in the quiet, shadowy regions of space, known as nebulae, where the seeds of stars are sown. Picture a dense cloud of gas and dust, drifting silently in space, waiting for the right conditions to ignite. These clouds, often enriched with the remnants of previous generations of stars, are the cradles of stellar birth. A disturbance, perhaps a shock wave from a nearby supernova or a collision with another cloud, sets the process in motion. As gravity takes hold, clumps within the cloud grow denser and hotter, forming protostars, the precursors to fully formed stars. But why do some of these protostars grow into brilliant giants while others remain as faint, failed stars? The answer lies in their mass. The mass of a star is the single most important factor in its life story. It determines how brightly it will burn, how long it will shine, and how spectacularly, or quietly, it will die. For now, however, we focus on the marvel of ignition, the moment when nuclear fusion begins. Deep within the core of a newborn star, temperatures rise to millions of degrees. Hydrogen atoms, the simplest and most abundant element in the universe, are fused into helium, releasing an enormous amount of energy. This energy radiates outward, creating the light and heat that we perceive as a star. From this moment, a delicate equilibrium is established. The inward pull of gravity is perfectly balanced by the outward push of radiation pressure. The star enters the longest and most stable phase of its life, known as the main sequence. Every star you see twinkling in the night sky is, or once was, in this main sequence phase. Some, like our sun, are moderate in size and will live billions of years in relative stability. Others, far more massive, burn through their fuel in just a few million years, destined for a much more dramatic demise. The difference lies in the rate at which they consume their nuclear fuel, a process that ties their brightness and temperature to their mass. Stars are not just isolated entities. They are cosmic engines driving the evolution of the universe. As they live and die, they release elements into the surrounding space, creating the raw materials for planets, moons, and even life itself. The carbon in your DNA, the calcium in your bones, and the iron in your blood were all forged in the heart of a star. In this sense, every atom of our existence is connected to these luminous giants. As we embark on this exploration of stellar life and death, consider this. Every star tells a story. It speaks of the forces that shaped it, the battles it fought to stay alive, and the impact it left on the universe long after its light faded. These stories are written in the language of light, gravity, and fusion, and they remind us of the profound interconnectedness of all things in the cosmos. The question remains, what happens when the balance is broken? When gravity overpowers pressure, or vice versa? the life of a star changes course dramatically. As we continue, we'll delve into the cosmic nurseries where stars are born, the fiery processes that sustain them, and the spectacular phenomena that signal their end. But for now, look up at the night sky and consider. Every star you see is living through an ancient dance of creation and destruction, and its story is far more complex and beautiful than we ever imagined. The cosmic nursery, stellar formation in nebulae. Imagine drifting through the vast emptiness of space and encountering a cloud so massive and dense that it stretches across light years. Within this seemingly tranquil expanse lies the birthplace of stars. These regions, known as nebulae, are far from empty. They teem with gas, dust, and the potential to ignite into the blazing beacons that will one day light up the universe. But what is it about these cosmic nurseries that gives rise to stars? And why does such profound creation emerge from the quiet darkness of the void? The process begins in the coldest, darkest regions of space, within what astronomers call molecular clouds. These are the densest portions of nebulae, rich in molecular hydrogen and other elements. They are often remnants of ancient stars that lived and died billions of years ago, spreading their material into the cosmos. But a molecular cloud in itself isn't enough to birth a star. Something must disturb its delicate equilibrium, causing it to collapse under its own gravity. The catalyst for this collapse can come in many forms. Perhaps it's the shockwave from a nearby supernova, a dying star's final act of violence. Or maybe it's the gravitational pull from a passing celestial body or the collision of two clouds. Once triggered, the chain reaction begins. Gravity takes hold, pulling the gas and dust inward, creating pockets of higher density called clumps. As these clumps grow denser, they fragment into smaller regions, each destined to become a star. This fragmentation is one of nature's most efficient methods of creation. A single molecular cloud, spanning tens or hundreds of light years, can give rise to thousands of stars, ranging in size and mass. Within these clumps, the interplay between gravity and pressure becomes the defining force in shaping a star's destiny. Deep within the collapsing cloud, the temperature and pressure begin to rise. As matter continues to fall inward, it gains kinetic energy, which is converted into heat. The clump evolves into what astronomers call a protostar, a faint, hot object surrounded by a swirling disk of gas and dust. This disk is not just a byproduct. It holds the raw material that may later form planets, moons, and other celestial companions. Protostars are fascinating objects. They are shrouded in a thick envelope of gas and dust, making them nearly invisible to optical telescopes. Instead, astronomers study them using infrared and radio waves, which can penetrate these veils and reveal the secrets within. What they've discovered is a chaotic environment where violent jets of gas shoot outward, magnetic fields twist and churn, and powerful winds push material away. But a protostar is not yet a star. To cross that threshold, it must ignite nuclear fusion in its core. This moment, the true birth of a star, requires immense pressure and temperature. For fusion to occur, the core must reach at least 10 million Kelvin, a feat achievable only by the relentless force of gravity. Once fusion begins, hydrogen atoms are converted into helium, releasing an enormous amount of energy in the process. This energy creates outward pressure that halts the inward collapse, stabilizing the protostar and marking its transformation into a full-fledged star. Not all clumps in a molecular cloud achieve this fate. Some lack the mass to reach the critical temperature and pressure needed for fusion. These objects, known as brown dwarfs, are often referred to as failed stars. They glow faintly due to residual heat from their formation, but never achieve the brilliance of true stars. Despite their dimness, brown dwarfs play a vital role in the galactic ecosystem, existing in a gray area between stars and planets. As stars ignite within a nebula, they begin to influence their surroundings. The intense radiation and stellar winds from massive young stars sculpt the remaining gas and dust, creating breathtaking structures. This is why nebulae like the Orion Nebula or the Eagle Nebula appear as intricate, colorful works of art. They are snapshots of the ongoing dance between creation and destruction, where stars shape their birthplace even as they emerge from it. But not all stars are born equal. The mass of a star at birth determines its future. Massive stars, many times the size of our sun, burn brighter and live shorter lives, often ending in spectacular supernovae. Smaller stars, like red dwarfs, burn their fuel slowly and can last for tens of billions of years. This diversity ensures that nebulae produce a cosmic symphony of stars, each contributing to the universe in its unique way. As we leave the cosmic nursery, we are left with a sense of awe at the delicate balance required to birth stars. From the interplay of gravity and pressure to the influence of external forces, the process is both chaotic and ordered, destructive and creative. And yet, it is through this complexity that the universe brings forth its most luminous creations. But what happens once a star is born? How does it sustain itself for millions or billions of years? To answer this, we must journey deeper into the anatomy of stars, exploring the nuclear processes that power them and the intricate systems that keep them alive. Every star carries within it a story of energy, balance, and transformation, stories that illuminate the vastness of the cosmos. The anatomy of a star, understanding their inner workings. At first glance, stars seem like simple points of light dotting the night sky, but beneath their luminous surface lies a world of extraordinary complexity. Stars are dynamic engines of energy, powered by processes so extreme that they defy the limits of what we experience on Earth. Have you ever wondered what keeps a star burning for millions or even billions of years? What hidden forces allow these celestial giants to maintain their brilliance and stability despite the immense gravitational pressure threatening to collapse them? To understand a star, one must first explore its layered structure. Though stars vary in size, temperature, and luminosity, their basic anatomy is strikingly similar. They are spherical objects, composed mostly of hydrogen and helium, with an internal architecture governed by the interplay of gravity, pressure, and energy production. This balance is essential to their survival and defines the nature of their lives. At the very heart of a star lies its core, the powerhouse where nuclear fusion occurs. In this region, temperatures soar to millions of degrees, and pressures reach unimaginable levels. Here, hydrogen nuclei collide with such force that they overcome their natural repulsion and fuse into helium, releasing vast amounts of energy in the form of light and heat. This process, known as the proton-proton chain reaction in smaller stars like our Sun, or the CNO cycle in massive stars, is the star's primary energy source. The energy generated in the core not only sustains the star, but also creates the outward pressure needed to counteract the inward pull of gravity. Surrounding the core is the radiative zone, a region where energy travels outward through the slow, diffusive movement of photons. The density in this zone is so high that photons are constantly absorbed and re-emitted by particles, taking thousands, even millions, of years to escape. This process ensures that the energy from the core is gradually transported outward, maintaining the star's stability. Beyond the radiative zone lies the convective zone, where energy transfer occurs through convection. Hot gases rise, cool, and sink in a dynamic, churning motion. This region is particularly active in smaller stars like red dwarfs, where convection dominates, but even in larger stars, it plays a crucial role in transporting energy to the star's surface. The surface of a star, called the photosphere, is where light is finally free to escape into space. It is the visible layer we see from Earth, and its temperature determines the star's color. Cooler stars appear red, while hotter stars glow blue or white. The photosphere is a delicate region, often marked by sunspots, temporary dark areas caused by magnetic activity, and granules, the visible tops of convection cells that create a mottled appearance. Above the photosphere lies the chromosphere, a thin, less dense layer that glows faintly in a reddish hue. Further out is the corona, the star's outer atmosphere, extending millions of kilometers into space. The corona is surprisingly hot, much hotter than the photosphere, a phenomenon that still puzzles scientists. This outer region produces the solar wind, a stream of charged particles that flows outward into space, influencing planetary atmospheres and magnetic fields. But what keeps these layers in harmony? The answer lies in the delicate balance between gravity and pressure, often referred to as hydrostatic equilibrium. Gravity pulls the star's material inward, threatening collapse, while the pressure from nuclear fusion pushes outward, creating a stable structure. This balance is not permanent. As a star ages and its core runs out of fuel, this equilibrium shifts, leading to dramatic changes in its life cycle. Another key feature of stars is their magnetic field. Generated by the motion of charged particles within the star, magnetic fields can influence everything from stellar winds to flares and eruptions. These fields are particularly prominent in stars like the Sun, where they create phenomena such as solar storms and coronal mass ejections, capable of affecting entire planetary systems. Stars are also classified by their size, temperature, and luminosity, categories that reveal much about their inner workings. The Hertzsprung-Russell (HR) diagram is a tool astronomers use to understand this relationship. It plots stars based on their luminosity and surface temperature, showing distinct groupings such as main sequence stars, giants, and white dwarfs. A star's position on this diagram reflects its stage in the stellar life cycle and its mass, the ultimate determinant of its fate. The mass of a star influences how efficiently it burns its nuclear fuel. Massive stars burn through their fuel quickly, living shorter, more intense lives, while smaller stars like red dwarfs burn slowly, lasting tens of billions of years. This variation in energy output and lifespan adds to the diversity of stars we see in the universe, from dim, long-lived red dwarfs to short-lived, brilliant supergiants. Stars are not isolated entities. They are profoundly interconnected with their surroundings. The energy and particles they emit contribute to the formation of planets, the evolution of galaxies, and even the conditions necessary for life. Every star is a factory of elements, producing heavier atoms like carbon, oxygen, and iron, which are released into space when the star dies. These elements become part of new stars, planets, and ultimately, living beings. When you gaze at a starry sky, remember that the light you see is the product of intricate processes occurring in a distant, fiery core. Stars are not just points of light. They are cosmic laboratories, transforming simple hydrogen into the complex elements that make up our universe. Their inner workings are a testament to the power of nature's laws, a constant reminder of the profound forces shaping the cosmos. But what happens when a star's core begins to run out of fuel? How does this intricate system adapt when its primary energy source is depleted? As we continue, we'll explore the next stages of a star's life, from its prime years as a main sequence star to the transformations that occur as it ages. Every star, no matter how bright or enduring, faces a moment when it must evolve or die. The Hertzsprung-Russell diagram, charting stellar life. If the universe were a library, stars would be its books, each with its own unique story written across billions of years. But how do astronomers make sense of these countless stories? How do they categorize stars and track their life cycles in a way that reveals the broader narrative of stellar evolution? Enter the Hertzsprung-Russell diagram, a revolutionary tool that forever changed how we understand the life and death of stars. This seemingly simple graph is the Rosetta Stone of stellar astronomy, a map that charts a star's journey from birth to its ultimate fate. The Hertzsprung-Russell diagram, or HR diagram for short, was independently developed in the early 20th century by Danish astronomer Ejnar Hertzsprung and American astronomer Henry Norris Russell. It is a two-dimensional plot that organizes stars based on two fundamental properties: their luminosity, brightness, and their surface temperature, color. These attributes are not just arbitrary. They are windows into the inner workings and evolutionary stages of a star. To grasp the significance of the HR diagram, let's first break down its axis. The vertical axis represents a star's luminosity, often measured relative to the Sun. A star that is 10 times brighter than the Sun will sit higher on the chart, while dimmer stars fall lower. The horizontal axis, intriguingly, is reversed. Cooler stars are plotted on the right and hotter stars on the left. This unconventional setup reflects the relationship between a star's temperature and its color. Hot blue stars on one end and cooler red stars on the other. When stars are plotted on the HR diagram, a remarkable pattern emerges. Most stars, including our Sun, fall along a diagonal band called the main sequence. This region is where stars spend the majority of their lives, steadily fusing hydrogen into helium in their cores. The main sequence stretches from the hot, massive, and luminous stars in the upper left to the cool, faint, and long-lived stars in the lower right. This arrangement reveals a crucial truth. A star's position on the main sequence is determined by its mass. The main sequence is not a random collection of points. It is a timeline. Stars enter the main sequence when they begin nuclear fusion and gradually move along it as they age. For massive stars, this journey is swift and dramatic, while smaller stars meander slowly, burning their fuel at a leisurely pace. The HR diagram captures these differences, allowing astronomers to estimate a star's age, mass, and energy output simply by noting its position. But not all stars remain on the main sequence forever. As a star depletes the hydrogen in its core, it undergoes profound changes that shift its position on the HR diagram. The direction of this movement depends on the star's mass and its next evolutionary phase. For low to medium mass stars, like our Sun, the depletion of hydrogen marks the end of the main sequence phase. With fusion in the core ceasing, gravity takes over, causing the core to contract and heat up. This triggers the fusion of hydrogen in a shell surrounding the core, causing the star's outer layers to expand. The star swells into a red giant, moving upward into the right on the HR diagram. During this phase, the star's brightness increases dramatically, even as its surface temperature drops. Massive stars, on the other hand, take a different path. These stars burn through their hydrogen rapidly, moving off the main sequence in a matter of millions of years. When their cores exhaust hydrogen, they begin fusing heavier elements like helium, carbon, and oxygen in a series of increasingly unstable cycles. On the HR diagram, these stars shift to the upper right, becoming supergiants. Their immense brightness and size make them some of the most visually striking objects in the universe. The later stages of a star's life also leave distinct imprints on the HR diagram. For low-mass stars, the red giant phase culminates in the ejection of the outer layers, forming a planetary nebula. What remains is a white dwarf, the dense, cooling remnant of the star's core. White dwarfs occupy the lower left corner of the HR diagram, characterized by high temperatures but low luminosity due to their small size. In contrast, massive stars face a more explosive fate. Their cores eventually collapse under gravity, leading to a supernova. Depending on the remaining mass, the star may become a neutron star or a black hole, objects that fall off the standard HR diagram entirely, as they no longer emit light in the conventional sense. The HR diagram is more than just a map of individual stars. It is a cosmic census. By studying the distribution of stars on the diagram, astronomers can infer the properties of entire star clusters and galaxies. For example, in young star clusters, most stars lie on the main sequence, reflecting their youth. In older clusters, the upper portion of the main sequence is conspicuously absent, as the more massive stars have already evolved into giants or remnants. This phenomenon, known as the main sequence turnoff, provides a powerful tool for determining the age of star clusters. The HR diagram also reveals the diversity of stars. While main sequence stars dominate, the diagram showcases outliers like red giants, supergiants, and white dwarfs, each representing a different chapter in the stellar life cycle. It highlights the interconnectedness of stars, showing how they share a common origin yet diverge into a multitude of paths based on their mass and composition. Perhaps most importantly, the HR diagram connects the seemingly abstract physics of stars to their observable characteristics. It translates the extreme processes occurring deep within a star, nuclear fusion, gravitational collapse, radiative transfer, into a visual representation that is both intuitive and profound. It reminds us that stars are not just distant lights in the sky. They are living entities with life cycles governed by the same fundamental laws that shape our world. As we move forward, we'll delve deeper into the main sequence phase, the longest and most stable period of a star's life. What sustains a star during this time, and how does it prepare for the changes to come? The HR diagram has provided the roadmap, but the journey through a star's life is just beginning. Main sequence stars, the prime of stellar life. Every star begins its life with a dramatic burst of energy, but it soon settles into a stable routine, much like a person reaching adulthood. This is the main sequence phase, a star's golden age. For millions to billions of years, stars shine steadily, converting hydrogen into helium through nuclear fusion and maintaining a delicate balance between the opposing forces of gravity and radiation pressure. But what makes this stage so stable, and why do stars spend most of their lives in this phase? To understand the main sequence, we must first revisit the forces at play within a star. Gravity, the universal force that pulls all matter together, constantly tries to compress the star into a smaller and denser sphere. Left unchecked, this would lead to catastrophic collapse. However, the star resists this fate through the outward pressure generated by nuclear fusion. At its core, the intense temperatures and pressures cause hydrogen nuclei to fuse into helium, releasing energy in the process. This energy, radiating outward, counteracts gravity's inward pull, creating a stable equilibrium known as hydrostatic balance. The duration of a star's main sequence phase depends on its mass. Massive stars, burning with incredible brightness, consume their nuclear fuel at a much faster rate than smaller stars. These luminous giants, such as blue supergiants, may spend only a few million years on the main sequence before evolving into more unstable phases. In contrast, smaller stars like red dwarfs are remarkably efficient, burning their fuel slowly and steadily. These stars can remain on the main sequence for tens to hundreds of billions of years, far exceeding the current age of the universe. Our own Sun is a classic example of a main sequence star. Classified as a G-type star, it has been shining for about 4.6 billion years and is expected to remain stable for another 5 billion years. During this time, the Sun converts approximately 600 million tons of hydrogen into helium every second, producing the energy that sustains life on Earth. Yet, even this seemingly steady star is gradually changing. As it fuses hydrogen into helium, its core becomes denser and hotter, causing the Sun to grow slightly brighter over time, a process that will eventually contribute to the transformation of our planet's environment. Main sequence stars come in a dazzling array of sizes, colors, and luminosities. These variations are governed by their mass, the fundamental characteristic that determines a star's fate. The most massive stars, located at the upper left of the Hertzsprung-Russell diagram, are hot, blue, and incredibly bright. These O and B-type stars have surface temperatures exceeding 30,000 Kelvin and radiate energy at rates thousands to millions of times that of the Sun. Their intense luminosity makes them some of the most prominent stars in the night sky, but their lifespans are tragically short, ending in dramatic supernovae. In stark contrast, stars at the lower right of the diagram, like M-type red dwarfs, are cool, dim, and long-lived. These stars have surface temperatures of less than 3,500 Kelvin and are often too faint to be seen with the naked eye. Despite their modest appearance, red dwarfs are the most common type of star in the universe, comprising about 70% of all stars. Their remarkable longevity ensures that they will continue to illuminate the cosmos long after more massive stars have burned out. The color of a star during its main sequence phase provides valuable clues about its temperature and composition. Blue stars are the hottest, emitting most of their energy in the ultraviolet spectrum, while red stars are cooler and radiate primarily in the infrared. In between, yellow stars like our Sun strike a balance, shining in the visible spectrum and appearing white or yellow to the human eye. Main sequence stars are also dynamic laboratories where the elements of the universe are forged. While hydrogen to helium fusion dominates this phase, heavier stars begin to produce trace amounts of other elements through secondary reactions like the CNO, carbon-nitrogen-oxygen, cycle. These elements, although minor in quantity, play a critical role in the evolution of stars and the formation of planetary systems. Binary and multi-star systems add another layer of complexity to the main sequence phase. Many stars are not solitary like the Sun, but exist in pairs or groups. In such systems, the gravitational interaction between stars can lead to fascinating phenomena, including mass transfer and even the merger of two stars. These interactions can dramatically alter a star's evolution, pushing it off the main sequence earlier than it would in isolation. As stable as the main sequence may seem, it is not without its challenges. Stars experience subtle variations in brightness and activity, often driven by magnetic fields and convection within their outer layers. In our Sun, these variations manifest as the solar cycle, an approximately 11-year pattern of sunspots, flares, and coronal mass ejections. While such activity is relatively mild for a star of the Sun's size, it can have profound effects on planets, influencing their atmospheres and climates. Another phenomenon worth noting is the eventual depletion of hydrogen in the star's core. This marks the beginning of the end for a main sequence star. When hydrogen runs out, the core contracts under gravity, heating up and igniting new fusion reactions in surrounding layers. This shift destabilizes the star, causing it to expand into a red giant or, for more massive stars, evolve into a supergiant. The precise path a star takes after the main sequence depends on its mass, composition, and the interactions it has experienced over its lifetime. As we conclude our exploration of the main sequence, it's clear that this phase represents the height of a star's life, a time of stability, productivity, and brilliance. It is during this phase that stars shine their brightest, support planetary systems, and contribute to the cosmic alchemy that enriches the universe. Yet, like all things in nature, this phase is finite. The end of the main sequence is not a conclusion, but a transition, setting the stage for the next, often more dramatic, chapters of a star's existence. What happens when a star begins to exhaust its nuclear fuel? How does its structure change, and what spectacular transformations lie ahead? In the next chapter, we will examine the role of mass in determining a star's fate, uncovering the divergent paths that stars take as they leave the main sequence and move toward their final stages. The role of mass in determining fate. When we think of stars, it's easy to imagine them as distant, unchanging points of light. Yet their life cycles are anything but static. A star's journey through life, from its birth in a cosmic nursery to its eventual death, hinges on a single, defining characteristic: its mass. This one variable determines whether a star will shine for billions of years or burn out in a fleeting, brilliant explosion. But how exactly does mass influence a star's fate? And why does it lead to such drastically different outcomes? At its core, the mass of a star governs the delicate balance between gravity and pressure. More massive stars experience stronger gravitational forces, leading to higher core pressures and temperatures. This accelerates the process of nuclear fusion, the engine that powers a star's light and heat. On the other hand, lower mass stars experience weaker gravitational compression, allowing them to burn their nuclear fuel more slowly and methodically. This fundamental relationship explains why massive stars live fast and die young, while smaller stars enjoy far longer, quieter lives. Let's begin by examining low-mass stars, the most common type in the universe. These include red dwarfs, stars with masses ranging from about 0.08 to 0.5 times that of the Sun. Red dwarfs are remarkably efficient at burning their hydrogen fuel, thanks to their lower core temperatures and extended lifespans. Unlike larger stars, which burn through their hydrogen in distinct layers, red dwarfs fully mix their fuel, ensuring no hydrogen is wasted. As a result, they can shine for tens to hundreds of billions of years, far longer than the current age of the universe. In fact, no red dwarf has yet reached the end of its life since the dawn of the cosmos. When a red dwarf does approach the end of its life cycle, it won't die in a dramatic fashion. Instead, it will quietly fade into a white dwarf, cooling slowly over trillions of years. This subdued ending reflects the star's modest beginnings and its efficient, slow-burning nature. Medium-mass stars, like our Sun, fall into a different category. With masses between 0.5 and about 8 times that of the Sun, these stars shine brighter and hotter than red dwarfs, but at the cost of a shorter lifespan. The Sun, for example, has a total lifespan of about 10 billion years, of which it is currently halfway through. During this time, it steadily fuses hydrogen into helium in its core, maintaining the balance between gravity and radiation pressure. However, when the hydrogen in the core is depleted, the balance begins to shift. Gravity takes over, causing the core to contract and heat up. This triggers the fusion of hydrogen in a shell surrounding the core, while the outer layers of the star expand dramatically. The star swells into a red giant, a phase marked by its enormous size and cooler surface temperature. For the Sun, this will mean engulfing the inner planets, possibly including Earth, in its bloated outer layers. The red giant phase is relatively brief, lasting only a few million years. As the star continues to fuse helium and other heavier elements in its core, it becomes increasingly unstable. Eventually, it ejects its outer layers, creating a spectacular planetary nebula, a shell of glowing gas illuminated by the remaining stellar core. What's left is a white dwarf, a dense, Earth-sized remnant composed mostly of carbon and oxygen. Over trillions of years, this white dwarf will cool and dim, fading into a black dwarf, a theoretical end state that the universe has not yet had time to produce. For high-mass stars, the story is entirely different. With masses exceeding 8 times that of the Sun, these giants burn their fuel at an astonishing rate, often exhausting their hydrogen reserves in just a few million years. Their immense gravitational pressure raises core temperatures high enough to fuse heavier elements like carbon, oxygen, silicon, and eventually iron. Each successive stage of fusion releases less energy, causing the star to become increasingly unstable. The fusion of iron marks a critical turning point. Unlike lighter elements, iron cannot release energy through fusion. Instead, it absorbs energy. When the core becomes dominated by iron, the star can no longer sustain the outward pressure needed to counteract gravity. In a fraction of a second, the core collapses, triggering a supernova explosion, a cataclysmic event that outshines entire galaxies. What remains after the supernova depends on the mass of the star's core. If the core is between 1.4 and about 3 times the mass of the Sun, it becomes a neutron star, a city-sized object so dense that a sugar cube-sized piece of its material would weigh billions of tons. Neutron stars often exhibit extreme magnetic fields and rapid rotation, emitting beams of radiation that we detect as pulsars. For the most massive stars, with cores exceeding 3 solar masses, even neutron degeneracy pressure cannot halt the collapse. These stars become black holes, regions of space-time so warped by gravity that nothing, not even light, can escape. Black holes are among the most mysterious and awe-inspiring objects in the universe, representing the ultimate endpoint of stellar evolution. The role of mass extends beyond individual stars. It also influences the dynamics of binary and multi-star systems. In binary systems where one star is significantly more massive than its companion, fascinating interactions can occur. For example, the massive star may evolve into a red giant, transferring material onto its smaller companion. This can lead to novae, in which the companion temporarily reignites nuclear fusion on its surface, or even the formation of a type Ia supernova if the companion exceeds a critical mass. Massive stars also play a pivotal role in enriching the universe with heavy elements. During their lifetimes, they produce elements up to iron through fusion, and their explosive deaths scatter these elements into space. The debris from supernovae seeds the formation of new stars, planets, and even life itself. Without massive stars, the universe would lack many of the essential ingredients for complexity. In essence, the mass of a star is its cosmic fingerprint, dictating not only its physical characteristics but also its interactions with the surrounding universe. From the gentle fading of red dwarfs to the violent explosions of supernovae, the diversity of stellar fates reflects the profound influence of mass on the life cycles of stars. As we move forward, we'll explore the next stages of stellar evolution, focusing on the dramatic transformations that occur as stars leave the main sequence. What happens when stars grow unstable? How do they evolve into giants or supergiants? And what lessons can we learn from their spectacular transitions? Giants and supergiants, the evolution beyond stability. The life of a star, no matter how serene it may seem during its main sequence phase, is destined for upheaval. As hydrogen in the core is exhausted, the delicate balance between gravity and pressure begins to falter, setting the stage for dramatic transformations. Stars evolve into giants or supergiants, swelling to colossal sizes and entering a phase of instability that marks the twilight of their existence. But what drives this transition? And why do some stars become majestic red giants while others balloon into luminous supergiants? To understand this phase, we must first revisit the core processes of a star. During its main sequence, a star fuses hydrogen into helium in its core, producing the energy needed to counteract gravity's inward pull. However, this nuclear fusion is not infinite. Eventually, the hydrogen fuel is depleted, and the fusion process grinds to a halt in the core. With no outward pressure to oppose gravity, the core begins to collapse, triggering profound changes throughout the star. As the core contracts, it heats up dramatically, reaching temperatures high enough to ignite a new round of nuclear fusion in the surrounding shell of hydrogen. This shell-burning phase generates an enormous amount of energy, causing the star's outer layers to expand. The result is a red giant, a star that has swollen to many times its original size, but has a cooler surface temperature, giving it a reddish hue. For stars like the Sun, this transformation into a red giant is the beginning of the end. The expansion of the outer layers is accompanied by a loss of mass, as stellar winds strip material away from the star. At the same time, the contracting core heats further, eventually reaching temperatures sufficient to ignite helium fusion. This marks a temporary period of stability, known as the helium flash, during which the star fuses helium into carbon and oxygen. However, helium fusion is far less efficient than hydrogen fusion, and the star quickly exhausts its helium supply. Without a new source of energy, the core contracts again, reigniting hydrogen fusion in the surrounding shells. This cycle of contraction and fusion creates complex layers within the star, with each layer burning progressively heavier elements. For stars of the Sun's mass, this process ends with the formation of a dense carbon-oxygen core surrounded by expelled outer layers, creating a planetary nebula and leaving behind a white dwarf. But what about more massive stars? Their fates are far more dramatic. Stars with masses exceeding 8 times that of the Sun follow a similar path initially, but their greater mass and gravity allow them to reach core temperatures high enough to fuse elements far beyond helium. These stars evolve into supergiants, swelling to sizes hundreds or even thousands of times greater than the Sun. Betelgeuse, for instance, is a red supergiant that, if placed in our solar system, would extend beyond the orbit of Jupiter. The sheer size and luminosity of supergiants make them some of the most extraordinary objects in the universe, but their brilliance comes at a cost. These stars burn through their fuel at an astonishing rate, creating an increasingly unstable core. As helium fusion gives way to the fusion of heavier elements like carbon, oxygen, neon, and silicon, the star builds up an onion-like structure, with each layer burning a different element. This process continues until the star attempts to fuse iron in its core. Unlike lighter elements, the fusion of iron does not release energy. Instead, it consumes it. This marks the beginning of the end for the supergiant. With no energy to counteract gravity, the core collapses in a matter of seconds, triggering a supernova explosion. This catastrophic event ejects the outer layers of the star into space, leaving behind either a neutron star or a black hole, depending on the mass of the core. The transition to a giant or supergiant phase is not merely a spectacle of size and luminosity. It is also a time of profound change in the star's environment. The intense radiation and stellar winds from these swollen stars sweep through surrounding space, sculpting nebulae and triggering the formation of new stars. In this way, the death throes of one generation of stars sow the seeds for the next. The mass of a star plays a critical role in determining whether it becomes a red giant or a supergiant. Stars with masses between 0.5 and 8 times that of the Sun will expand into red giants, shedding their outer layers to reveal a white dwarf core. More massive stars, on the other hand, follow the path to supergiants, their immense gravitational force allowing them to fuse heavier elements and meet a more explosive end. Interestingly, not all stars in the giant phase appear red. Some, known as blue giants or blue supergiants, have extremely high surface temperatures and emit a brilliant blue light. These stars are often in transition, shedding mass and evolving into red supergiants or, in rare cases, collapsing directly into supernovae without the red supergiant stage. Blue supergiants are among the hottest and most luminous stars in the universe. Yet their instability makes them short-lived. One of the most famous examples of a blue supergiant is Rigel, the brightest star in the constellation Orion. Rigel is a massive star nearing the end of its life, and its eventual fate is likely to be a supernova, leaving behind a neutron star or black hole. As stars evolve into giants or supergiants, they become increasingly unstable, prone to eruptions, pulsations, and mass loss. These phenomena create spectacular sights in the night sky, such as the pulsations of Cepheid variables, which serve as cosmic yardsticks for measuring distances in the universe. The variability of these stars is directly tied to the processes occurring within their cores and outer layers, making them invaluable tools for understanding stellar evolution. The giant and supergiant phases also play a crucial role in enriching the cosmos. The heavy elements forged in the cores of these stars are released into space during their final stages, contributing to the chemical diversity of the universe. These elements become the building blocks for new stars, planets, and even life itself. In this sense, the death of a star is not an ending, but a transformation, a passing of the torch to the next generation of celestial bodies. As we leave the realm of giants and supergiants, we are drawn to the remnants they leave behind. What becomes of a star after it sheds its outer layers or explodes in a supernova? How do these remnants, white dwarfs, neutron stars, and black holes, continue to influence the universe long after the light of the original star has faded? White dwarfs, the quiet aftermath of low-mass stars. When a low to medium-mass star reaches the end of its journey, it doesn't go out in a dramatic explosion like its more massive counterparts. Instead, it undergoes a quieter, more subtle transformation, leaving behind a white dwarf, a dense, dim, and cooling remnant that holds the final chapter of the star's story. But what exactly is a white dwarf? How does it form, and why does it play such a pivotal role in the life cycle of the universe? To understand the birth of a white dwarf, we must first revisit the final stages of a star like our Sun. As it depletes the hydrogen in its core, the star expands into a red giant, fusing helium into carbon and oxygen. This phase is marked by intense instability, as the star sheds its outer layers in a series of pulsations and stellar winds. The result is a glowing shell of gas, known as a planetary nebula, surrounding the hot, dense core that remains. At the heart of this planetary nebula lies the nascent white dwarf. Without the pressure from nuclear fusion to counteract gravity, the core collapses into an incredibly compact object, about the size of Earth but with a mass comparable to that of the Sun. This extraordinary density means that a teaspoon of white dwarf material would weigh several tons on Earth. The formation of a white dwarf marks a star's transition from an active energy producer to a cooling remnant. Unlike its earlier life stages, a white dwarf no longer generates energy through fusion. Instead, it shines faintly due to residual heat left over from its collapse. Over billions of years, this heat gradually dissipates, and the white dwarf cools and dims, eventually becoming a cold, dark object known as a black dwarf. However, the universe is not yet old enough for any black dwarfs to have formed. Even the oldest white dwarfs are still glowing faintly. The physics governing white dwarfs is both fascinating and extreme. As the core contracts, the star's electrons are squeezed into a state known as electron degeneracy. This phenomenon, dictated by the Pauli exclusion principle, states that no two electrons can occupy the same quantum state simultaneously. As a result, the electrons exert a powerful outward pressure that prevents further collapse, balancing the inward pull of gravity. This degeneracy pressure is what keeps a white dwarf stable, despite the immense gravitational forces acting upon it. However, there is a limit to how much mass a white dwarf can support. Known as the Chandrasekhar limit, this threshold is approximately 1.4 times the mass of the Sun. If a white dwarf's mass exceeds this limit, it can no longer resist gravitational collapse and may undergo a dramatic transformation. In binary star systems, for instance, a white dwarf can accumulate material from a companion star. If it reaches the Chandrasekhar limit, the intense pressure and temperature can reignite nuclear fusion, triggering a Type I supernova, a brilliant explosion that completely obliterates the white dwarf and releases vast amounts of energy. White dwarfs are not just remnants. They are also timekeepers of the cosmos. Because their cooling rate is predictable, astronomers can use white dwarfs as cosmic clocks to estimate the ages of star clusters and the galaxy itself. By studying populations of white dwarfs, researchers have gained critical insights into the history and evolution of the Milky Way. Despite their dimness, white dwarfs are far from unremarkable. They often exhibit intriguing phenomena, such as pulsations caused by their cooling processes. Some white dwarfs are magnetized, with magnetic fields billions of times stronger than Earth's, creating exotic environments that challenge our understanding of physics. Others, known as white dwarf binaries, interact dynamically with companion stars, producing dramatic events like novae, temporary outbursts of light caused by the sudden ignition of accumulated material on the white dwarf surface. In rare cases, white dwarfs can merge with one another in binary systems. The result of such a merger depends on the combined mass. If the total mass exceeds the Chandrasekhar limit, the merger may produce a Type I supernova or even a neutron star. If the mass remains below the limit, the resulting white dwarf may become unusually massive and exhibit peculiar characteristics, such as unusual chemical compositions. The presence of white dwarfs in planetary systems also raises intriguing questions about the fate of planets. As a star evolves into a red giant, it often engulfs or disrupts nearby planets. However, distant planets can survive this process, continuing to orbit the white dwarf. Some white dwarfs even show evidence of planetary debris in their atmospheres, suggesting that remnants of planetary systems can persist long after the star's demise. Our own sun will one day become a white dwarf. After exhausting its hydrogen and helium fuel, it will shed its outer layers, leaving behind a dense carbon-oxygen core. Over billions of years, this remnant will cool and fade, a faint beacon in the vast expanse of space. The fate of Earth and the other planets is less certain. While inner planets like Mercury and Venus will likely be engulfed, the outer planets and any surviving moons may continue to orbit the cooling white dwarf for eons. White dwarfs represent a humbling stage in the life of a star. They remind us that even the most brilliant celestial objects are finite, destined to fade and cool over time. Yet, they also underscore the cyclical nature of the universe. The material ejected during the formation of a planetary nebula enriches the surrounding space, providing the building blocks for new stars, planets, and perhaps even life. As we leave behind the quiet aftermath of low-mass stars, we turn our attention to the dramatic remnants of more massive stars. What happens when the immense gravitational forces of a collapsing star give rise to an object even denser than a white dwarf? How do neutron stars emerge? And what makes them some of the most extreme objects in the universe? Neutron stars, the powerhouses of stellar remnants. When a massive star reaches the end of its life and exhausts the nuclear fuel at its core, it faces a dramatic and violent demise. For stars that are too massive to leave behind a white dwarf but not quite massive enough to collapse into a black hole, the result is one of the most extreme objects in the universe, a neutron star. These dense, rapidly spinning remnants defy ordinary understanding of matter, packing the mass of the sun into a sphere no larger than a city. But what makes neutron stars so extraordinary? And how do they influence the universe long after their parent stars have perished? The story of a neutron star begins with the catastrophic collapse of a massive star's core. As the star's core runs out of elements that can undergo fusion, such as carbon, oxygen, and silicon, gravity overwhelms any remaining outward pressure. In a matter of seconds, the core implodes, compressing its material to an incredibly dense state. Electrons are forced into protons, creating neutrons and releasing a flood of neutrinos, subatomic particles that escape the star and carry away vast amounts of energy. The implosion is halted by neutron degeneracy pressure, a quantum mechanical force similar to the electron degeneracy pressure that stabilizes white dwarfs. This pressure arises from the Pauli exclusion principle, which prevents neutrons from occupying the same quantum state. The result is a neutron star, a compact, ultra-dense object with a radius of about 10 to 15 kilometers, but a mass up to 2 or 3 times that of the Sun. To put this into perspective, a sugar cube-sized piece of neutron star material would weigh billions of tons on Earth. The newly formed neutron star is often born spinning rapidly, with rotation periods as short as a few milliseconds. This rapid spin is a consequence of the conservation of angular momentum, as the star's core shrinks dramatically in size during its collapse. Additionally, neutron stars possess extraordinarily strong magnetic fields, billions to trillions of times more powerful than Earth's. These fields play a crucial role in the behavior and emissions of the neutron star. One of the most fascinating phenomena associated with neutron stars is the pulsar. Pulsars are neutron stars that emit beams of electromagnetic radiation from their magnetic poles. As the neutron star spins, these beams sweep across space like the beam of a lighthouse. If the beams happen to align with Earth, we observe them as regular pulses of light or radio waves. Pulsars are some of the most precise timekeepers in the universe, with their pulses occurring at incredibly regular intervals. Astronomers have even used pulsars as cosmic clocks to test theories of relativity and detect gravitational waves. The discovery of pulsars in the late 1960s revolutionized our understanding of neutron stars. Initially mistaken for signals from extraterrestrial civilizations, the pulses were soon identified as the emissions of rotating neutron stars. Since then, thousands of pulsars have been discovered, revealing the diversity and complexity of these remarkable objects. Beyond pulsars, neutron stars exhibit other extreme behaviors. Some neutron stars, known as magnetars, have magnetic fields so intense that they can distort atomic structures and generate powerful bursts of X-rays and gamma rays. These bursts, called soft gamma repeaters, are among the most energetic events observed in the universe. Magnetars are rare and short-lived compared to other neutron stars, as their intense magnetic fields decay over time. Neutron stars also play a crucial role in binary systems. When paired with a companion star, a neutron star can accrete material from its partner, forming an accretion disk. As this material spirals toward the neutron star, it heats up and emits X-rays, creating an X-ray binary. In some cases, the infalling material can even reignite nuclear fusion on the surface of the neutron star, leading to bursts of X-rays known as Type 1 X-ray bursts. The most spectacular events involving neutron stars occur when two of them collide. These mergers, often triggered by the gradual decay of their orbits due to gravitational wave emission, produce an explosion called a kilonova. Kilonovae are not only visually stunning, but also critical to the production of heavy elements like gold, platinum, and uranium. The detection of gravitational waves from neutron star mergers in recent years has provided unprecedented insights into these events, confirming their role as cosmic factories for the universe's heaviest elements. Despite their incredible density and power, neutron stars are not invincible. If a neutron star accretes enough material or merges with another massive object, its mass can exceed the Tolman-Oppenheimer-Volkoff limit, the maximum mass that neutron degeneracy pressure can support. When this happens, the neutron star collapses further, forming a black hole. This transition represents the final stage in the life of a massive star, marking the boundary between matter as we understand it and the unknown. The study of neutron stars offers profound insights into the nature of matter, gravity, and the universe itself. These objects represent a unique laboratory for testing the laws of physics under conditions that cannot be replicated on Earth. From the quantum mechanics of degeneracy pressure to the relativistic effects of their intense gravity, neutron stars challenge and expand our understanding of the cosmos. As we leave behind the realm of neutron stars, we approach the ultimate endpoint of stellar evolution: black holes. What happens when gravity completely overwhelms all opposing forces? How do black holes bend the very fabric of space-time, and what mysteries lie within their event horizons? Black holes, the final frontier of stellar collapse. Among the many remnants of dying stars, none is as mysterious and awe-inspiring as the black hole. These enigmatic objects represent the ultimate victory of gravity, regions of space where matter is so densely packed that not even light can escape. But what exactly is a black hole? How do they form? And what secrets do they hold about the nature of space, time, and the universe itself? A black hole forms when the core of a massive star collapses under its own gravity, surpassing the limits of neutron degeneracy pressure that support neutron stars. This happens when the core's mass exceeds approximately 3 times the mass of the Sun, triggering an unstoppable implosion. The result is a singularity, a point of infinite density where the known laws of physics break down, surrounded by an event horizon, the boundary beyond which nothing can escape. The event horizon defines the size of a black hole, often measured by its Schwarzschild radius. For a black hole with the mass of the Sun, this radius would be just a few kilometers. Despite their small size, black holes exert an immense gravitational pull, warping space-time and drawing in everything that ventures too close, including light. This creates the iconic black appearance for which they are named. Black holes come in different sizes, broadly categorized into 3 types: stellar mass black holes, intermediate black holes, and supermassive black holes. Stellar mass black holes, formed from the collapse of individual stars, typically range from a few to tens of solar masses. These are the most common type and are often found in binary systems, where they interact with companion stars, accreting matter and emitting X-rays in the process. Intermediate black holes, with masses between 100 and 100,000 solar masses, are more elusive. They are thought to form through the merger of smaller black holes or the collapse of massive star clusters. Recent observations of gravitational waves have provided tantalizing evidence of their existence, but their formation and abundance remain areas of active research. Supermassive black holes, the giants of the cosmic stage, reside at the centers of most galaxies, including our own Milky Way. With masses ranging from millions to billions of times that of the Sun, these behemoths are thought to have formed through the merging of smaller black holes and the accretion of vast amounts of matter over cosmic time. The supermassive black hole at the center of the Milky Way, known as Sagittarius A*, has a mass of about 4 million suns and plays a crucial role in the dynamics of our galaxy. The gravitational pull of a black hole is so intense that it affects the very fabric of space-time. According to Einstein's theory of general relativity, black holes create deep wells in space-time, bending the paths of nearby objects and light. This effect, known as gravitational lensing, allows astronomers to detect black holes indirectly by observing the way they warp the light from background stars and galaxies. One of the most striking features of black holes is the accretion disk, a swirling ring of gas and dust that spirals toward the event horizon. As matter falls into the black hole, it heats up due to friction and gravitational energy, emitting intense radiation in the process. These emissions, often in the form of X-rays and gamma rays, make accreting black holes some of the brightest objects in the universe, despite their dark cores. But what lies inside a black hole? This question has puzzled scientists for decades, as the conditions within the event horizon defy conventional physics. The singularity, where density and gravity are infinite, is a realm where our current understanding of the universe breaks down. To fully comprehend black holes, we need a unified theory of quantum mechanics and gravity, a goal that remains one of the greatest challenges in modern physics. Black holes are not merely destructive entities. They also play a key role in shaping the universe. Their immense gravity influences the formation and evolution of galaxies, regulating star formation and driving the growth of cosmic structures. Supermassive black holes, in particular, generate powerful jets of charged particles that extend thousands of light years into space, sculpting the intergalactic medium and contributing to the cosmic web of matter. The study of black holes has advanced rapidly in recent years, thanks to breakthroughs in observational technology. In 2019, the Event Horizon Telescope captured the first-ever image of a black hole's event horizon, revealing the shadow of a supermassive black hole in the galaxy M87. This achievement confirmed decades of theoretical predictions and opened a new era of black hole astrophysics. Gravitational wave astronomy has also revolutionized our understanding of black holes. The detection of gravitational waves from black hole mergers by observatories like LIGO and Virgo has provided direct evidence of their existence and behavior. These ripples in space-time, caused by the collision of 2 black holes, carry information about their masses, spins, and distances, offering new insights into their origins. Despite these advances, black holes remain a source of profound mystery. Do they truly destroy all information about the matter they consume, as suggested by the information paradox? Could black holes be gateways to other universes or dimensions, as some theories propose? And what happens at the singularity, where time and space themselves cease to exist? As we delve deeper into the nature of black holes, we are confronted with questions that challenge the very foundations of physics. These cosmic enigmas remind us of the limits of our knowledge and the boundless possibilities that lie beyond. They are not just the remnants of dying stars, but also windows into the fundamental workings of the universe. From the quiet aftermath of white dwarfs to the extremes of neutron stars and the final frontier of black holes, the life and death of stars reveal a universe in constant transformation. But even as stars die, their remnants continue to shape the cosmos, enriching space with the elements of life, bending space-time, and fueling the cycle of creation and destruction. Supernovae, the explosive death of stars. The life of a star is a tale of immense energy, constant transformation, and eventual decline. But for the universe's more massive stars, their demise is not a quiet fading into darkness. It's a spectacular explosion that outshines entire galaxies. This event, known as a supernova, is one of the most dramatic phenomena in the cosmos, signaling the death of a star while also seeding the universe with elements necessary for new stars, planets, and even life itself. But what triggers a supernova? How does this cataclysmic event unfold? And why is it so vital to the universe? Supernovae are classified into two main types, based on the mechanisms that trigger them: Type 1 and Type 2. These categories further divide into subtypes, but at their core, the difference lies in the presence or absence of hydrogen in the star's outer layers and the processes that lead to the explosion. Type 2 supernovae, the death of massive stars. Type 2 supernovae occur when a massive star, at least 8 times the mass of the Sun, exhausts its nuclear fuel. Throughout its life, such a star fuses lighter elements like hydrogen and helium into progressively heavier elements, creating a layered onion-like structure in its core. This process continues until the core is dominated by iron. Iron is a turning point in the life of a massive star because it cannot release energy through fusion. As a result, the star loses its primary source of outward pressure, and gravity takes over. In a matter of seconds, the core collapses to a fraction of its size, creating a neutron star or black hole. This implosion sends shockwaves rippling outward, causing the outer layers of the star to explode into space with incredible force. The energy released in a Type 2 supernova is staggering. For a brief moment, the exploding star outshines its entire galaxy. The blast also produces a burst of neutrinos, nearly massless subatomic particles, that carry away a significant portion of the star's energy. These neutrinos play a crucial role in powering the explosion and provide vital clues about the processes occurring within the collapsing core. The remnants of a Type 2 supernova are as varied as they are fascinating. The core may become a neutron star or, if massive enough, collapse further into a black hole. The outer layers, meanwhile, are ejected into space, creating stunning nebulae like the Crab Nebula, which is the remnant of a supernova observed in 1054 AD. These remnants are not just visually spectacular. They are also rich in heavy elements like carbon, oxygen, and iron, which are essential for the formation of planets and life. Type 1 supernovae, a thermonuclear explosion. Type 1 supernovae, in contrast, are not the result of a single massive star's death but occur in binary systems, where 2 stars orbit a common center. In particular, Type Ia supernovae involve a white dwarf, a dense remnant of a low to medium mass star, that accretes material from its companion star. As the white dwarf accumulates matter, its mass gradually increases. If it approaches the Chandrasekhar limit, about 1.4 times the mass of the Sun, the intense pressure and temperature reignite nuclear fusion. This runaway fusion reaction consumes the white dwarf in a fraction of a second, producing an explosion that completely obliterates the star. Type I supernovae are unique in their consistency. Because the explosion always occurs at roughly the same critical mass, the brightness of a Type I supernova is remarkably uniform. This property has made them invaluable tools for measuring cosmic distances and understanding the expansion of the universe. Observations of type I supernovae in distant galaxies provided the first evidence for dark energy, the mysterious force driving the accelerated expansion of the universe. The role of supernovae in cosmic evolution. Supernovae are not just the dramatic endpoints of stellar life. They are also engines of cosmic change. The explosive ejection of a star's outer layers spreads heavy elements like calcium, nickel, and gold throughout the interstellar medium. These elements, forged in the intense heat and pressure of the supernova, become the building blocks of future stars, planets, and even living organisms. In this sense, supernovae are both destroyers and creators, ensuring that the universe remains dynamic and evolving. The shockwaves from supernovae also play a role in triggering new star formation. As the blast wave moves through space, it compresses nearby clouds of gas and dust, initiating the gravitational collapse that leads to the birth of new stars. This cyclical relationship between stellar death and creation is a cornerstone of galactic evolution, ensuring that matter is constantly recycled and repurposed. The observable impact of supernovae. Supernovae are so bright that they can be observed even in distant galaxies. Historically, they have been recorded by astronomers and civilizations around the world, often appearing as guest stars in the night sky. Modern telescopes, equipped with advanced detectors, allow astronomers to study supernovae in unprecedented detail, capturing their light curves, spectra, and even the chemical signatures of their remnants. One of the most famous supernovae in recent history is SN 1987A, located in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. Observed in 1987, this Type II supernova provided valuable insights into the processes leading to core collapse and the role of neutrinos in the explosion. It also left behind a neutron star, or black hole, though its exact nature remains a subject of ongoing investigation. More recently, astronomers have used space-based observatories like Hubble and Chandra to study supernovae and their remnants. These observations have revealed the complex interactions between supernova shockwaves and the surrounding interstellar medium, producing intricate and beautiful structures. The mystery of hypernovae and gamma-ray bursts. For the most massive stars, the energy of a supernova can be even more extreme, producing what is known as a hypernova. These explosions release 10 times the energy of a typical supernova and are often associated with long gamma-ray bursts, intense flashes of gamma radiation that can last for seconds or minutes and are detectable across billions of light years. Gamma-ray bursts, particularly the long-duration type, are thought to result from the collapse of massive stars into black holes. As material falls into the black hole, it produces powerful jets of particles and radiation that escape along the star's rotational axis. These bursts are among the most energetic events in the universe and serve as beacons of extreme astrophysical processes. The supernova legacy. The explosive death of stars is a reminder of the universe's relentless cycle of destruction and creation. Supernovae end the lives of stars but pave the way for new ones, scattering the seeds of heavy elements that are vital for the complexity and diversity of the cosmos. They shape galaxies, influence the formation of planetary systems, and provide the raw materials for life itself. As we move forward in exploring the remnants of these extraordinary events, we turn our attention to the quieter, denser remnants of stellar collapse. What happens when a massive explosion leaves behind a core so compact that it defies normal matter? In the next chapter, we'll dive into the exotic phenomena of hypernovae and gamma-ray bursts, where the boundaries of stellar death are pushed to their most extreme limits. Hypernovae and gamma-ray bursts, extreme endings. When stars die, their fates are written by the forces that define their lives: gravity, mass, and the elemental fusion that powered them. Among these stellar deaths, the most massive stars in the cosmos experience endings so extreme that they defy comprehension. Hypernovae, the titanic explosions of the largest stars, and gamma-ray bursts, the most energetic events in the universe, represent the ultimate expressions of stellar demise. But what causes these phenomena, and what do they reveal about the universe's most violent processes? Hypernovae, the titans of stellar death. A hypernova is an exceptionally powerful supernova, with energy output far exceeding that of its more common counterparts. These events are triggered by the collapse of stars with initial masses exceeding 30 times that of the Sun. When such a star reaches the end of its life, its core collapses directly into a black hole, while its outer layers are ejected in an explosion of unparalleled intensity. Hypernovae release energies on the order of 10 to the power of 45 joules, or roughly 10 times the energy of a typical Type II supernova. The enormous gravitational forces of the collapsing core drive the creation of powerful shockwaves that rip through the star's outer layers, generating a bright, energetic explosion visible across vast cosmic distances. For a brief period, a hypernova can outshine its host galaxy, releasing more energy in seconds than the Sun will emit over its entire 10 billion-year lifespan. One of the distinguishing features of hypernovae is the production of heavy elements far beyond what is typical for supernovae. These explosions forge exotic isotopes and scatter them across interstellar space, enriching the surrounding medium with the raw materials for new stars, planets, and potentially life. The link between hypernovae and gamma-ray bursts. Hypernovae are closely associated with long gamma-ray bursts, GRBs, which are intense flashes of gamma radiation lasting from a few seconds to several minutes. GRBs are among the brightest events in the universe, capable of releasing more energy in a few seconds than the Sun will emit over billions of years. These bursts are so powerful that they can be detected from billions of light years away, making them invaluable tools for studying the early universe. The leading model for long GRBs is the collapsar scenario, in which a rapidly rotating massive star collapses into a black hole. As the star's core collapses, material falling into the black hole forms an accretion disk, releasing enormous amounts of energy. This energy drives relativistic jets, beams of particles moving at nearly the speed of light, that punch through the star's outer layers and into space. When these jets align with Earth, we observe a gamma-ray burst. The afterglow of a GRB, which can last for days or weeks in X-rays, visible light, and radio waves, provides additional insights into the environment surrounding the burst. By studying these afterglows, astronomers have learned about the nature of the collapsing star, the structure of its jets, and the composition of the interstellar medium. Short gamma-ray bursts and neutron star mergers. Not all gamma-ray bursts are linked to hypernovae. Short gamma-ray bursts, lasting less than 2 seconds, are thought to result from the merger of two neutron stars or a neutron star and a black hole. These cataclysmic collisions, which occur after billions of years of orbit decay, driven by gravitational waves, release a burst of gamma rays along with gravitational wave signals detectable by observatories like LIGO and Virgo. The detection of gravitational waves from a neutron star merger in 2017, accompanied by a short gamma-ray burst and a kilonova explosion, confirmed this model. These events not only produce gamma rays, but also forge heavy elements like gold and platinum, enriching the universe in a process called R-process nucleosynthesis. Observing hypernovae and gamma-ray bursts. Hypernovae and gamma-ray bursts are rare, but incredibly significant events. Observing them requires specialized instruments capable of detecting high-energy emissions. Space-based telescopes like NASA's Swift and Fermi Gamma-Ray Space Telescope are designed to capture the fleeting gamma-ray signals and rapidly alert ground-based observatories to study their afterglows. Because gamma-ray bursts are detectable across vast cosmic distances, they serve as beacons for studying the early universe. Some GRBs originate from stars that lived and died within a few 100 million years of the Big Bang, providing a glimpse into the formation of the first stars and galaxies. These observations help astronomers understand the conditions of the universe during its infancy. The legacy of hypernovae and gamma-ray bursts. The violent deaths of massive stars and hypernovae and the intense energy of gamma-ray bursts leave lasting imprints on the cosmos. The heavy elements forged in these events enrich the interstellar medium, contributing to the chemical diversity necessary for the formation of planets and life. The shockwaves from hypernovae can trigger the collapse of nearby gas clouds, sparking the birth of new stars and continuing the cycle of stellar evolution. Gamma-ray bursts also challenge our understanding of fundamental physics. The extreme conditions in the jets and accretion disks around black holes provide natural laboratories for studying high-energy particle interactions, relativistic effects, and magnetic fields. These events push the limits of our models, offering insights into the behavior of matter and energy under the most extreme conditions. Hypernovae, GRBs, and the future of exploration. As our observational capabilities improve, the study of hypernovae and gamma-ray bursts promises to deepen our understanding of the universe. Future missions like the James Webb Space Telescope and next-generation gamma-ray observatories will allow astronomers to probe these events in greater detail, uncovering their origins, environments, and impact on cosmic evolution. Hypernovae and gamma-ray bursts remind us of the immense power and complexity of the universe. They are not just the violent endpoints of stellar life, but also crucial drivers of cosmic change, enriching the universe and shaping its structure. These extraordinary phenomena serve as a testament to the dynamic interplay of creation and destruction that defines the cosmos. As we leave behind the cosmic extremes of hypernovae and gamma-ray bursts, we turn our focus to the quieter, but equally transformative effects of stellar winds and outflows. How do these phenomena shape the galaxies we see today, and what role do they play in the ongoing cycle of stellar birth and death? Stellar winds and their role in galactic evolution. While the death of stars often grabs the spotlight with explosive finales like supernovae and gamma-ray bursts, the quieter processes that unfold during their lifetimes can be just as transformative for the cosmos. Stellar winds, the steady streams of charged particles ejected from stars, play a pivotal role in shaping galaxies, enriching the interstellar medium, and driving the cycle of stellar birth and death. But what exactly are stellar winds, and why are they so critical to the evolution of the universe? The basics of stellar winds. Stellar winds are continuous outflows of gas from the outer layers of a star. These winds are composed primarily of ions, electrons, and neutral particles, and they vary dramatically in strength and composition depending on the type and age of the star. While all stars produce stellar winds to some degree, the intensity and effects of these winds are determined by factors such as the star's mass, temperature, and evolutionary stage. For stars like the Sun, stellar winds are relatively gentle, with particles escaping at speeds of a few hundred kilometers per second. These solar winds, driven by the high temperatures and dynamic magnetic fields in the Sun's corona, extend throughout the solar system, shaping planetary magnetospheres and creating phenomena like the auroras on Earth. In contrast, massive stars such as O and B-type stars and red supergiants produce far more powerful winds. These high-energy outflows, driven by intense radiation pressure and strong magnetic fields, can reach velocities of thousands of kilometers per second, carrying away significant amounts of mass over the star's lifetime. These stellar winds are not just a byproduct of the star's activity. They are critical agents of change in their environments. The role of stellar winds in stellar evolution. For massive stars, stellar winds significantly influence their life cycles and ultimate fates. These winds strip away the star's outer layers, reducing its mass and altering the balance between gravity and radiation pressure. This mass loss can determine whether a star ends its life as a neutron star, a black hole, or a completely disrupted remnant. For example, the progenitors of long gamma-ray bursts are thought to be massive, rapidly rotating stars that have lost their hydrogen and helium envelopes due to intense stellar winds. Without this mass loss, the stars might collapse differently, leading to less energetic explosions or entirely different end states. In red giants and supergiants, stellar winds also play a critical role in shaping the surrounding environment. As these stars shed their outer layers, they create vast shells of gas and dust that can eventually form planetary nebulae or feed into the interstellar medium. This process redistributes heavy elements forged in the star's core, enriching the galaxy with the building blocks for new stars and planets. The impact on the interstellar medium. One of the most profound effects of stellar winds is their contribution to the interstellar medium, the vast reservoir of gas and dust that fills the space between stars. Stellar winds inject energy, momentum, and heavy elements into this medium, influencing its density, temperature, and composition. Over time, these processes shape the structure and dynamics of galaxies. In regions of active star formation, stellar winds from young, massive stars can compress nearby gas clouds, triggering the gravitational collapse that leads to the birth of new stars. At the same time, these winds can also disrupt star formation by blowing away gas and dust, creating cavities and bubbles in the interstellar medium. The balance between these opposing effects, stimulating and inhibiting star formation, determines the rate at which galaxies evolve. In some cases, stellar winds interact with supernova shock waves, amplifying their effects and driving large-scale flows of gas across galactic scales. These interactions can create intricate structures, such as the filaments and shells seen in nebulae, and can even expel material from galaxies entirely, contributing to the enrichment of the intergalactic medium. The diversity of stellar winds. The nature of stellar winds varies greatly across different types of stars. For instance, solar-type stars. Stars like the Sun produce solar winds, driven by the high temperatures and magnetic activity of their outer atmospheres. These winds are relatively low in mass loss but extend far into space, shaping planetary environments and influencing space weather. Massive stars. O and B-type stars produce intense radiation-driven winds, ejecting large amounts of material at high velocities. These winds are critical in shaping the star's evolution and the surrounding interstellar medium. Red giants and supergiants. These stars produce slow but dense winds, driven by pulsations and radiation pressure on dust grains. The material lost during this phase contributes to the formation of planetary nebulae and the enrichment of the interstellar medium. Wolf-Rayet stars. These highly evolved, massive stars produce some of the most powerful winds in the universe, driven by their extreme luminosity and high temperatures. Wolf-Rayet stars lose mass at incredible rates, shedding their outer layers to reveal their hot, dense cores. Low-mass stars and red dwarfs. These stars produce weaker winds, but their longevity ensures that their cumulative contribution to the interstellar medium is significant over cosmic timescales. Observing stellar winds. Stellar winds are challenging to observe directly, but their effects can be seen in various ways. For example, astronomers use spectroscopy to detect the absorption lines created by winds as they interact with surrounding material. Infrared and radio observations reveal the dusty shells and outflows created by red giants and supergiants, while X-ray and ultraviolet telescopes capture the high-energy emissions from massive stars and their winds. One striking example of stellar wind activity is the creation of bow shocks, arc-shaped regions where stellar winds collide with the surrounding interstellar medium. These structures, often seen in massive stars moving through space, provide direct evidence of the interaction between stellar winds and their environments. Stellar winds and galactic evolution. On a galactic scale, stellar winds are a key driver of change. They regulate the cycle of star formation, shape the distribution of gas and dust, and enrich the galaxy with heavy elements. Over billions of years, these processes contribute to the evolution of galaxies, transforming them from primordial clouds of hydrogen and helium into the diverse and dynamic systems we see today. The impact of stellar winds is particularly evident in starburst galaxies, where intense episodes of star formation produce massive stars that drive powerful winds. These winds can create large-scale outflows, expelling gas and dust from the galaxy and quenching further star formation. Such feedback processes are essential for understanding the balance of star formation and gas depletion in galaxies across the universe. The quiet architects of the cosmos. While not as dramatic as supernovae or gamma-ray bursts, stellar winds are essential to the story of the universe. They are the quiet architects of change, shaping the environments where stars and planets form, redistributing the elements that make up everything we see, and driving the evolution of galaxies over cosmic time. As we turn our attention to the stars that never fully ignite, the brown dwarfs and failed stars, we will explore the boundary between stars and planets, delving into the curious cases where stellar winds are absent or minimal. What do these objects reveal about the nature of star formation, and how do they fit into the grand tapestry of the cosmos? Brown dwarfs, the stars that never were. Amid the dazzling variety of stars that populate the universe, there exists a curious category of objects that defy traditional classification. These are the brown dwarfs. sometimes referred to as failed stars. Too massive to be considered planets, yet too small to sustain the nuclear fusion that powers stars. Brown dwarfs occupy a gray area between these celestial bodies. But what are brown dwarfs, and what can they teach us about the boundaries of star formation and the diversity of objects in the cosmos? The formation of brown dwarfs. Brown dwarfs form in much the same way as stars. In the dense regions of molecular clouds, gravity pulls gas and dust together into clumps. If a clump accumulates enough mass, its core becomes hot and dense enough to ignite hydrogen fusion, marking the birth of a true star. However, if the clump's mass is below a critical threshold, about 0.08 times the mass of the Sun, the core temperature never reaches the 10 million Kelvin needed for hydrogen fusion. Instead, the object stabilizes as a brown dwarf. This failure to ignite fusion is what sets brown dwarfs apart from stars. Without the continuous energy source provided by fusion, brown dwarfs cannot sustain the same brightness or longevity as stars. Instead, they radiate heat left over from their formation, gradually cooling and fading over time. The characteristics of brown dwarfs. Brown dwarfs vary widely in size, temperature, and brightness, but they share certain key characteristics. Typically, they have masses between 13 and 80 times that of Jupiter. Too small for hydrogen fusion, but large enough to sustain limited fusion of deuterium, a heavy isotope of hydrogen, or lithium during their early stages. This brief fusion period distinguishes brown dwarfs from planets, which never experience fusion at all. The surface temperatures of brown dwarfs range from a few thousand Kelvin in their youth to a few hundred Kelvin as they cool. This cooling causes their colors to shift from red to infrared, making them difficult to detect with optical telescopes. Instead, astronomers rely on infrared observations to identify and study brown dwarfs. Spectroscopically, brown dwarfs show unique signatures. They lack the hydrogen fusion line seen in stars, but exhibit absorption features from molecules like methane, water vapor, and ammonia, features more commonly associated with planets. This molecular composition provides clues about their atmospheres and physical conditions. The discovery of brown dwarfs. The existence of brown dwarfs was theorized long before they were observed. In the 1960s, astronomers realized that objects smaller than a certain mass would fail to ignite hydrogen fusion, leading to the concept of substellar objects. However, it wasn't until the 1990s that the first brown dwarfs were definitively identified, thanks to advances in infrared astronomy. Two groundbreaking discoveries marked this era. The first was Tide 1, found in 1995 in the Pleiades star cluster, and the second was Gliese 229b, a companion to a nearby star. These discoveries confirmed that brown dwarfs are a distinct class of objects, bridging the gap between stars and planets. Since then, thousands of brown dwarfs have been discovered in star-forming regions, stellar clusters, and even as isolated objects in interstellar space. They are now thought to be as numerous as stars, though their faintness and low temperatures make them challenging to detect. Brown dwarfs and planetary systems. Brown dwarfs are often found in binary systems, orbiting a more massive star. In such cases, they behave much like planets, reflecting light from their stellar companion and occasionally showing evidence of atmospheres and weather patterns. However, some brown dwarfs exist independently, wandering the galaxy as solitary objects. The line between brown dwarfs and massive planets is blurred. Objects with masses between 13 and 25 times that of Jupiter can form in two ways: through gravitational collapse, like stars, or through accretion within a protoplanetary disk, like planets. This overlap challenges traditional definitions and highlights the complexity of classifying celestial objects. The role of brown dwarfs in galactic evolution. Although they lack the dramatic influence of stars, brown dwarfs contribute to the galactic ecosystem in subtle ways. Their formation processes provide insights into the conditions within molecular clouds and the factors that determine whether a clump of gas becomes a star, a brown dwarf, or a planet. By studying their atmospheres, astronomers gain clues about the chemistry of the interstellar medium and the diversity of planetary atmospheres. Brown dwarfs also serve as laboratories for studying objects at the boundary of fusion. The limited deuterium and lithium fusion in brown dwarfs offers a glimpse into the processes that govern the transition from stellar to planetary behavior. These studies help refine our models of star formation and the evolution of substellar objects. Brown dwarfs as proxies for exoplanets. The study of brown dwarfs has important implications for exoplanet research. Because they share many physical and atmospheric characteristics with gas giants, brown dwarfs provide a testing ground for theories about planetary formation and behavior. Their relative proximity and lack of a bright stellar companion make them ideal targets for detailed spectroscopic analysis, revealing insights into atmospheric dynamics, cloud formation, and weather patterns. For example, observations of variability in brown dwarf brightness suggest the presence of storms and atmospheric features, similar to Jupiter's Great Red Spot. These findings provide a preview of what astronomers might find when studying distant exoplanets with similar properties. The future of brown dwarf exploration. As observational techniques continue to improve, the study of brown dwarfs is poised to enter a new era. Upcoming telescopes like the James Webb Space Telescope, JWST, and the Extremely Large Telescope, ELT, will enable astronomers to probe the faintest and coolest brown dwarfs, uncovering details about their atmospheres, compositions, and formation histories. In addition to advancing our understanding of brown dwarfs, these studies will inform broader questions about the distribution of mass and energy in the galaxy. By mapping the populations of stars, brown dwarfs, and planets, astronomers can piece together a more complete picture of the universe's structure and evolution. The cosmic role of the stars that never were. Though they lack the brilliance and longevity of true stars, brown dwarfs are vital to the cosmic tapestry. They reveal the complexities of star formation, challenge our definitions of celestial objects, and bridge the gap between stars and planets. Their study reminds us that even the smallest and faintest objects have a role to play in the grand story of the universe. As we transition from the dim world of brown dwarfs, we turn our gaze to the intricate dynamics of binary star systems. What happens when two stars share a cosmic dance, influencing each other's evolution and sometimes producing spectacular phenomena? The interplay between stellar companions holds the key to some of the most fascinating processes in the universe. Binary stars and their complex relationships. While many stars, like our Sun, exist in solitude, a significant portion of the universe's stars are not solitary wanderers, but are instead locked in gravitational embraces with one or more stellar companions. Binary star systems, where two stars orbit a common center of mass, represent a dynamic and complex category of celestial phenomena. These stellar duos exhibit relationships that range from harmonious coexistence to dramatic interactions that shape their evolution and sometimes result in spectacular cosmic events. What governs these intricate stellar dances, and how do they influence the stars involved? The basics of binary systems. Binary star systems are classified based on their orbital configurations and the means by which astronomers detect them. These categories include 1. Visual binaries. Systems where both stars are separately visible through a telescope. These are often widely spaced pairs with long orbital periods, allowing direct observation of their motion. 2. Spectroscopic binaries. Systems detected through the Doppler shifts in their spectral lines, indicating their orbital motion. These systems are often too close for the stars to be resolved individually. 3. Eclipsing binaries. Systems where one star passes in front of the other from our perspective, causing periodic dips in brightness. These light curves provide valuable information about the star's sizes, masses, and orbital inclinations. 4. Astrometric binaries. Systems where the presence of a companion is inferred from the wobbling motion of the visible star, a subtle effect caused by their shared gravitational pull. Binary systems are further categorized based on the distance between the stars, which determines how they interact. In detached binaries, the stars are far enough apart to evolve independently. In semi-detached binaries, one star fills its Roche lobe, the region within which its gravitational pull dominates, and transfers material to its companion. In contact binaries, the stars are so close that they share a common envelope, often leading to significant mass exchange and complex interactions. The formation of binary systems. Binary systems form through processes similar to those of single stars, within the dense regions of molecular clouds. However, the dynamics of the collapsing gas clouds can result in the fragmentation of material, leading to the formation of multiple stellar cores that become gravitationally bound. The distribution of angular momentum during the collapse plays a crucial role. If the original gas cloud has significant angular momentum, it is more likely to produce a binary or multiple star system. These initial conditions, combined with the masses of the stars and their proximity, set the stage for the system's long-term evolution. The influence of binary interactions. Binary star systems are far from static. Their interactions can dramatically alter the fates of the stars involved. The effects of these interactions depend on the system's configuration and the evolutionary stages of the stars. Mass transfer and accretion. In semi-detached and contact binaries, mass transfer between the stars can reshape their evolution. As one star expands during its red giant phase, it overflows its Roche lobe, spilling material onto its companion. This process can rejuvenate the companion star, increasing its mass, luminosity, and temperature. The accreting star may even temporarily appear as a blue straggler, a star that seems younger than the rest of its stellar population. Mass transfer can also lead to the formation of accretion disks, where material spirals toward the recipient star. These disks emit intense radiation, particularly in the ultraviolet and X-ray wavelengths, and are key features in systems involving compact objects like white dwarfs, neutron stars, or black holes. Evolution toward cataclysmic events. Binary interactions often set the stage for some of the universe's most dramatic phenomena. For example, novae. When a white dwarf in a binary system accretes enough material from its companion, the added mass can reignite nuclear fusion on the surface, leading to a sudden, dramatic increase in brightness. This process does not destroy the white dwarf, allowing for repeated outbursts. Type Ia supernovae. If the white dwarf's mass approaches the Chandrasekhar limit, 1.4 times the Sun's mass, it undergoes a runaway fusion reaction, resulting in a powerful explosion that completely destroys the star. These supernovae are invaluable as standard candles for measuring cosmic distances. X-ray binaries. Systems where a neutron star or black hole accretes material from a companion often produce intense X-rays. These emissions provide insights into the extreme physics of compact objects, including their magnetic fields, spin rates, and accretion dynamics. Mergers and gravitational waves. In some cases, the orbits of binary stars decay over time due to the emission of gravitational waves, causing the stars to spiral toward each other. When the stars merge, the event can produce phenomena ranging from kilonovae, in the case of neutron star mergers, to the formation of more massive compact objects, such as black holes. The detection of gravitational waves from binary mergers by observatories like LIGO and Virgo has opened a new window into these extraordinary events, providing direct evidence of the dynamics of binary systems. Binary stars and stellar evolution. Binary stars evolve in ways that differ significantly from single stars. For example, common envelope evolution. When one star in a close binary system expands into its giant phase, it can engulf its companion in a shared envelope of gas. The drag forces within the envelope cause the stars to spiral closer together, often ejecting the envelope in the process. This phase can lead to the formation of compact binaries or trigger the merger of the two stars. Runaway stars. If one star in a binary system explodes as a supernova, the remaining star can be flung into space at high velocity, becoming a runaway star. These stars travel at extraordinary speeds and often end up far from their original locations. Triple and multiple systems. Many binaries are a part of larger systems, where gravitational interactions with a third star can destabilize the binary, causing eccentric orbits, collisions, or even ejections. Binary stars in context. Binary stars are not merely curiosities. They are crucial to our understanding of the universe. They provide a natural laboratory for testing astrophysical theories, from the physics of accretion and fusion to the behavior of matter in extreme gravitational fields. Observations of binary systems have also shed light on stellar populations, galactic dynamics, and the cosmic distribution of matter. One of the most famous binary systems is Sirius, the brightest star in the night sky, which consists of a main sequence star and a white dwarf companion. Another is Cygnus X1, one of the first confirmed black holes, identified by its X-ray emissions and its interaction with a massive companion star. The dance of binary stars. Binary stars remind us that the cosmos is a place of interaction and interconnectedness. Their gravitational dances shape their lives in ways that solitary stars can never experience, leading to phenomena that enrich the universe and deepen our understanding of its workings. As we transition from the dramatic interplay of binary stars, we turn our focus to their occasional, breathtaking outbursts. What happens when stars ignite anew after lying dormant for millennia? In the next chapter, we'll explore novae and their dazzling, temporary displays of light. Novae and their resplendent displays. Amid the seemingly eternal backdrop of stars in the night sky, there are occasional flashes of brilliance that remind us of the dynamic nature of the universe. These fleeting phenomena, known as novae, are among the most spectacular stellar events visible to the naked eye. Though they pale in comparison to the immense power of supernovae, novae offer their own unique insights into the delicate interplay between stars, the processes that sustain them, and the transitory beauty of the cosmos. But what exactly is a nova? How does it occur? And what makes it such a fascinating subject for astronomers? Understanding novae, the basics. A nova occurs in a binary star system, specifically one that includes a white dwarf and a companion star. The white dwarf, the dense remnant of a once luminous star, has an incredibly strong gravitational pull due to its compact size and high mass. If its companion is a main sequence star, red giant, or other type of active star, material from the companion can be drawn toward the white dwarf, forming an accretion disk, a swirling ring of gas and dust. Over time, hydrogen from the companion star accumulates on the surface of the white dwarf. As this layer grows thicker, the temperature and pressure at its base increase. Eventually, the conditions become extreme enough to trigger nuclear fusion, igniting the hydrogen in a runaway thermonuclear reaction. This explosion expels the outer layer of material into space, producing a sudden, dramatic increase in brightness, a nova. The characteristics of a nova. Novae are typically observed as sudden brightening events, often in stars that previously appeared faint or invisible. The brightness of a nova can increase by a factor of 10,000 or more, making it visible to the naked eye in some cases. This peak brightness is sustained for days to weeks, after which the nova gradually fades as the ejected material disperses and cools. The expelled material travels at speeds ranging from hundreds to thousands of kilometers per second, forming an expanding shell of gas and dust. These remnants are often visible as faint nebulae surrounding the white dwarf, providing a lasting reminder of the explosive event. Novae are classified into different types based on their recurrence and light curves. Classical novae. These occur when a white dwarf accumulates enough material for a single, explosive event. Classical novae may recur, but only after tens of thousands of years, depending on the rate of accretion. Recurrent novae. These novae involve white dwarfs with high accretion rates, leading to repeated outbursts on shorter timescales, often within decades. Examples include systems like RS Ophiuchi and T Pyxidus, which have produced multiple recorded eruptions. Dwarf novae. These are less energetic outbursts caused by changes in the accretion disk rather than thermonuclear explosions. They are common in cataclysmic variable star systems. The science behind the explosion. The physics of a nova explosion is a testament to the delicate balance of forces in stellar systems. The process begins with the slow accumulation of hydrogen from the companion star. As the hydrogen layer grows denser, the white dwarf's intense gravity compresses it, increasing the temperature until it reaches the critical point for fusion. This fusion is not like the steady process occurring in a star's core. Instead, it occurs in a runaway reaction, where the heat from fusion ignites adjacent layers of hydrogen, spreading across the surface of the white dwarf in a wave of thermonuclear fire. This chain reaction releases an immense amount of energy, propelling the outer layers of the star into space. Importantly, the white dwarf itself is not destroyed in the process. The explosion expels only the accumulated hydrogen, leaving the core intact and ready to begin the cycle again. This cyclic nature makes novae fascinating objects of study, as they offer repeated opportunities to observe the same system in action. Novae and their role in the universe. While novae are less energetic than supernovae, their impact on the surrounding environment is far from negligible. The material ejected during a nova enriches the interstellar medium with elements like carbon, nitrogen, and oxygen, contributing to the ongoing chemical evolution of the galaxy. Over time, this enrichment helps to form the building blocks for new stars, planets, and even life. The repeated cycles of novae also have implications for the evolution of binary star systems. In some cases, the mass transfer from the companion star to the white dwarf can destabilize the system, altering the orbits of the stars, or even leading to a merger. If the white dwarf gains enough mass to approach the Chandrasekhar limit, it may explode as a Type I supernova, leaving a far more dramatic legacy. Observing novae, a window into stellar physics. Novae have been observed for centuries, with some of the earliest recorded events dating back to ancient Chinese and Greek astronomers. Modern telescopes and instruments, however, have revolutionized our ability to study these phenomena in detail. Spectroscopy, in particular, reveals the chemical composition, velocity, and temperature of the ejected material, providing insights into the processes driving the explosion. Space-based observatories like the Hubble Space Telescope and the Chandra X-ray Observatory have captured stunning images of nova remnants, revealing intricate structures formed by the interaction of ejected material with the surrounding medium. Infrared observations, meanwhile, allow astronomers to study the dust and molecules formed in the aftermath of the explosion. The most famous novae. Several novae have captivated astronomers and the public alike. Nova Persei 1901, one of the brightest novae of the 20th century, visible to the naked eye and leaving behind a striking nebula known as GK Persei. RS Ophiuchi, a recurrent nova that has erupted multiple times in the past century, providing a rare opportunity to study the same system over successive events. V1500 Cygni, Nova Cygni 1975, a classical nova that became one of the brightest objects in the night sky, inspiring widespread interest in detailed studies. The beauty and transience of novae. Novae are a vivid reminder of the transient beauty of the cosmos. They illustrate the delicate balance of forces within binary systems and the dynamic processes that govern the life and death of stars. Though their light fades quickly, their impact endures, leaving traces in the interstellar medium and contributing to the ongoing evolution of the galaxy. As we move forward, we turn our attention to the remnants of stellar death and the profound role they play in shaping the universe. How do supernovae and novae forge the elements that make up everything we see, from planets to life itself? In the next chapter, we'll explore the cosmic alchemy of star death and its far-reaching consequences. The cosmic alchemy of star death, forging elements. The stars that light up the universe are not just luminous beacons in the night sky. They are factories of creation, forging the very elements that compose everything we see, touch, and experience. From the carbon in our cells to the oxygen we breathe, and even the gold in our jewelry, the materials that make up the world around us were born in the fiery crucibles of stars. But how do stars create these elements? What processes occur during their lives and deaths that enable this cosmic alchemy? To understand the profound role of stellar death in shaping the universe, we must delve into the heart of these celestial powerhouses. The origins of the elements. In the earliest moments of the universe, only the simplest elements existed. The Big Bang produced hydrogen, helium, and trace amounts of lithium, light elements that formed the building blocks for the first stars. But the heavier elements, the ones essential for planets and life, were absent. These were forged later, within stars, through a series of nuclear reactions collectively known as nucleosynthesis, hydrogen fusion, and the creation of helium. The simplest fusion process occurs in the cores of main-sequence stars like our Sun. Here, hydrogen nuclei, protons, combine under immense pressure and temperature to form helium, releasing vast amounts of energy in the process. This reaction, known as the proton-proton chain or the CNO cycle in more massive stars, is the primary source of a star's light and heat, helium fusion, and the birth of carbon. As a star exhausts its hydrogen fuel, it begins to fuse helium in its core, provided the core temperature reaches approximately 100 million Kelvin. This process, called the triple alpha reaction, involves 3 helium nuclei combining to form carbon. For stars slightly more massive than the Sun, this reaction can also produce oxygen, setting the stage for the creation of the heavier elements. The role of massive stars, element factories. Massive stars, with their higher core temperatures and pressures, can forge elements far beyond helium and carbon. These stars undergo successive stages of fusion, creating a layered structure resembling an onion, with each shell burning a different element. As the core temperature increases, new fusion processes ignite. Carbon fusion produces elements like neon, sodium, and magnesium. Neon fusion creates oxygen and magnesium. Oxygen fusion forms silicon, sulfur, and other intermediate elements. Silicon fusion, the final stage before core collapse, producing iron and nickel in the star's core. Iron marks the end of the line for stellar fusion. Unlike lighter elements, fusing iron does not release energy. Instead, it absorbs it. This inability to produce energy leads to the star's collapse, triggering a supernova explosion. Supernovae, the cosmic forge. When a massive star explodes as a supernova, the intense heat and pressure generated during the explosion enable the formation of elements heavier than iron, such as gold, platinum, and uranium. This process, known as rapid neutron capture, or the R process, occurs when nuclei capture neutrons faster than they can decay, creating heavy, neutron-rich isotopes. These isotopes eventually decay into stable elements, which are ejected into space along with the other material expelled during the explosion. Supernovae are the universe's most efficient distributors of heavy elements. The debris from these explosions enriches the interstellar medium, seeding future generations of stars and planets with the raw materials needed for complex chemistry and biology. Without supernovae, the universe would lack the diversity of elements required for the formation of terrestrial planets and the development of life. Neutron-star mergers and the production of heavy elements. In recent years, astronomers have discovered another significant source of heavy elements: neutron-star mergers. When 2 neutron stars in a binary system spiral together and collide, the resulting kilonova explosion releases enormous amounts of energy and material. The extreme conditions in these mergers are ideal for the R process, producing elements like gold and platinum in quantities that rival or exceed those formed in supernovae. The detection of gravitational waves from neutron star mergers, coupled with observations of their electromagnetic counterparts, has confirmed their role as major contributors to the universe's elemental diversity. These events highlight the interconnectedness of stellar evolution, as the remnants of massive stars continue to shape the cosmos long after their explosive deaths. Planetary nebulae and element dispersal. For stars like the Sun, which end their lives as white dwarfs, the process of enriching the universe is quieter, but no less important. As these stars shed their outer layers, they form planetary nebulae, glowing shells of gas and dust that disperse elements like carbon, nitrogen, and oxygen into space. While these elements are lighter than those produced in supernovae, they are essential for organic chemistry and life. The cosmic recycling process. The materials ejected during stellar deaths do not simply dissipate into the void. They become part of the interstellar medium, where they are incorporated into new generations of stars and planets. This cycle of stellar birth, death, and rebirth ensures that the universe becomes progressively richer in heavy elements over time, a process known as galactic chemical evolution. For example, our Sun is a second or third generation star, meaning it formed from a cloud of gas and dust enriched by previous generations of stars. The Earth and its abundance of heavy elements, from iron to gold, are direct beneficiaries of this cosmic recycling process. Life and the legacy of stellar death. The connection between stellar death and life is profound. The carbon in your DNA, the calcium in your bones, the iron in your blood, and the oxygen you breathe were all forged in stars that lived and died billions of years ago. Every atom of matter heavier than hydrogen and helium has a stellar origin, making each of us a walking testament to the creativity of the cosmos. This realization underscores the role of stars as the universe's great alchemists, transforming simple elements into the diverse building blocks of matter. Without the processes that occurred during stellar deaths, the universe would remain a barren expanse of hydrogen and helium, devoid of the complexity needed for planets, ecosystems, and consciousness. Observing the alchemy of the cosmos. Modern telescopes and instruments allow astronomers to trace the journey of elements across the universe. Spectroscopic studies of supernovae, planetary nebulae, and kilonovae reveal the chemical fingerprints of these events, providing direct evidence of nucleosynthesis in action. Observations of star-forming regions show how enriched gas and dust from previous generations of stars fuel the birth of new stellar systems. These studies not only deepen our understanding of the universe's past, but also help us predict its future. By mapping the distribution of elements and their origins, astronomers can reconstruct the history of galaxies and the processes that shape them. The eternal dance of creation and destruction. The alchemy of star death reminds us that the universe is a place of constant transformation. From the quiet dispersal of planetary nebulae to the violent explosions of supernovae and the extreme conditions of neutron star mergers, the cosmos is a dynamic interplay of creation and destruction. It is through this eternal dance that the universe evolves, building complexity and enabling the emergence of life. As we move forward, we shift our focus to the ethereal beauty of planetary nebulae and the fleeting ghosts of dying stars. How do these luminous remnants encapsulate the final stages of stellar evolution? And what stories do they tell about the stars that created them? Stellar ghosts, planetary nebulae, and their ethereal beauty. When stars like our Sun approach the end of their lives, they undergo a final transformation that leaves behind one of the most beautiful and ephemeral phenomena in the universe: planetary nebulae. These glowing shells of gas and dust are the delicate remnants of dying stars, expanding into space and shining with the energy of their central cores. While their name might misleadingly suggest a connection to planets, planetary nebulae are far more profound. Ethereal markers of a star's transition into its ultimate stage as a white dwarf. What creates these luminous structures, and what can they teach us about stellar evolution and the life cycle of matter in the cosmos? What are planetary nebulae? A planetary nebula forms when a star with a mass between 0.8 and 8 times that of the Sun reaches the end of its life. As these stars exhaust their nuclear fuel, they expand into red giants, shedding their outer layers through powerful stellar winds. Once the outer layers are lost, what remains is the star's hot, dense core, which emits intense ultraviolet radiation. This radiation ionizes the ejected gas, causing it to glow in vibrant colors, creating the spectacular display of a planetary nebula. The term planetary nebula originated in the 18th century, when astronomers using early telescopes noted their resemblance to the round shapes of distant planets like Uranus and Neptune. While we now know that these structures have no direct connection to planets, the name has endured. The life cycle of a planetary nebula. The formation of a planetary nebula begins in the red giant phase of a star's life. As the star's core contracts, its outer layers expand and cool, creating a luminous, bloated appearance. During this phase, the star sheds its outer layers through intense stellar winds, losing a significant fraction of its mass. Over time, these layers drift away, forming a shell of gas and dust around the star. Once the outer layers are fully ejected, the remaining core heats up, reaching temperatures of over 100,000 Kelvin. This core, known as a proto-white dwarf, emits high-energy ultraviolet photons that ionize the surrounding gas, causing it to glow. The colors of a planetary nebula are determined by the chemical composition of the ejected material. For example, hydrogen emits red or pink hues. Oxygen glows green or blue. Nitrogen produces deep reds. The nebula continues to expand over tens of thousands of years, eventually dispersing into the surrounding interstellar medium. By the time the central white dwarf cools and fades, the planetary nebula has dissipated, leaving behind only the compact remnant. Shapes and structures. The diversity of planetary nebulae. One of the most striking features of planetary nebulae is their incredible variety of shapes and structures. Far from being simple spheres, many planetary nebulae exhibit intricate and symmetrical patterns, including rings, hourglass shapes, bipolar lobes, and complex filaments. These shapes are thought to result from interactions between the ejected material, the star's rotation, magnetic fields, and the presence of binary companions. For instance, the Ring Nebula, M57, a classic example of a spherical planetary nebula, with a bright ring structure and a faint halo of material extending outward. The Cat's Eye Nebula, NGC 6543, known for its intricate concentric rings and symmetrical lobes, this nebula showcases the effects of periodic mass loss and stellar winds. The Butterfly Nebula, NGC 6302, a striking bipolar nebula with twin lobes of gas extending outward, shaped by a central star that may have interacted with a companion. Advances in observational technology, particularly with the Hubble Space Telescope, have revealed the extraordinary detail and complexity of these structures, challenging earlier models of their formation. The role of planetary nebulae in the cosmic ecosystem. While planetary nebulae are short-lived on cosmic timescales, typically lasting only 10,000 to 50,000 years, they play a critical role in enriching the interstellar medium. The material ejected during their formation contains elements like carbon, nitrogen, and oxygen, which were synthesized during the star's life. As this material disperses into space, it becomes part of the raw material for future generations of stars and planets. The study of planetary nebulae also provides valuable insights into the late stages of stellar evolution. By analyzing their spectra, astronomers can determine the chemical composition, velocity, and temperature of the ejected material, shedding light on the processes that govern mass loss and element production in aging stars. Observing planetary nebulae, celestial masterpieces. Planetary nebulae are among the most visually stunning objects in the night sky, making them popular targets for both professional astronomers and amateur stargazers. Many can be observed with modest telescopes, appearing as small, colorful clouds against the backdrop of stars. Some of the most famous examples include the Helix Nebula, NGC 7293, often called the Eye of God. This nearby planetary nebula is a sprawling structure visible in the constellation Aquarius. The Dumbbell Nebula, M27, one of the first planetary nebulae discovered. Its symmetrical, dumbbell-like shape makes it a favorite for observers. The Eskimo Nebula, NGC 2392, resembling a face surrounded by a parka, this nebula showcases intricate details and bright colors. Modern observatories, such as the Hubble Space Telescope and the Very Large Telescope, have captured high-resolution images of planetary nebulae, revealing their breathtaking beauty and the subtle interactions between gas, dust, and radiation. The legacy of planetary nebulae. Though their lifetimes are brief, planetary nebulae leave an enduring legacy. The elements they release into space contribute to the ongoing cycle of stellar birth and death, enriching the galaxy and enabling the formation of planets and, ultimately, life. The white dwarfs they leave behind serve as time capsules, preserving the history of the stars that created them. Our own sun will one day create a planetary nebula, providing a glimpse into the future of our solar system. Billions of years from now, as the sun sheds its outer layers, it will leave behind a glowing shell of gas illuminated by a cooling white dwarf, a quiet but beautiful testament to its life and death. The cosmic ghosts of dying stars. Planetary nebulae remind us of the fleeting nature of stellar life and the intricate processes that govern the cosmos. They are the ghosts of dying stars, shining brightly for a brief moment before fading into the vastness of space. Yet, in their transience, they enrich the universe with the elements of creation, ensuring that the cycle of life continues. As we transition from the beauty of planetary nebulae, we turn to the broader implications of stellar death and rebirth. How do the remnants of stars fuel the next generation of stellar formation? And what role do they play in the cyclical nature of the cosmos? In the next chapter, we'll explore the interconnectedness of stellar life and death. The cyclical nature of stellar life. The universe is a cosmic symphony, an endless dance of creation and destruction. Nowhere is this more evident than in the life and death of stars. These celestial objects are not isolated entities. They are part of a larger cycle that has shaped the universe for billions of years. From their birth in dense molecular clouds to their explosive deaths and quiet remnants, stars contribute to an ongoing process that ensures the constant renewal of matter and energy in the cosmos. How does this cycle work, and why is it so essential to the evolution of galaxies, planets, and life itself? The birthplace of stars, molecular clouds. The cycle of stellar life begins in vast molecular clouds, cold, dense regions of gas and dust that serve as the cradles of star formation. These clouds, often enriched with material from previous generations of stars, contain the raw ingredients needed to ignite stellar birth: hydrogen, helium, and traces of heavier elements like carbon, oxygen, and iron. When a molecular cloud becomes unstable due to gravitational forces, collisions with other clouds, or the shock waves from nearby supernovae, it begins to collapse under its own gravity. As the cloud fragments, it forms dense cores that heat up and eventually ignite nuclear fusion, giving birth to new stars. The presence of these heavier elements, forged in earlier stars, influences the properties of the newborn stars and their potential to host planetary systems. The lives of stars, fueling galactic evolution. As stars evolve, they play an active role in shaping their environments. Massive stars, with their intense radiation and powerful stellar winds, blow away surrounding gas and dust, carving out cavities in the interstellar medium. These winds can compress nearby gas clouds, triggering the formation of new stars in a process known as triggered star formation. Smaller stars, like red dwarfs, have a gentler impact on their surroundings, but contribute to the galaxy's overall evolution through their longevity and eventual enrichment of the interstellar medium. These quieter processes ensure that the galaxy remains a dynamic system, constantly replenished with new stars and elements. Stellar death, a catalyst for renewal. The death of a star marks the most dramatic phase of its life cycle, yet it is also the point at which the star gives back to the universe. Depending on its mass, a star's death can take several forms, each with unique contributions to the cosmic ecosystem. Low to medium-mass stars. Stars like our Sun end their lives by shedding their outer layers to form planetary nebulae, leaving behind dense white dwarfs. The material ejected during this process is rich in elements like carbon and nitrogen, which are essential for life. These elements are returned to the interstellar medium, where they can be incorporated into new stars and planets. Massive stars. The deaths of massive stars are far more dramatic. When these stars explode as supernovae, they release enormous amounts of energy, scattering heavy elements like iron, nickel, and gold into space. These explosions also generate shock waves that compress nearby gas clouds, kickstarting new waves of star formation. The remnants of these stars, such as neutron stars and black holes, continue to influence their surroundings through gravitational forces and energetic emissions. Neutron star mergers. The collision of neutron stars, another consequence of stellar death, produces kilonovae, explosions that generate some of the universe's heaviest elements, including gold and platinum. These events enrich the interstellar medium on a scale comparable to supernovae, ensuring that even the rarest elements are distributed across the cosmos. The role of the interstellar medium. The interstellar medium acts as the universe's recycling center, collecting the material ejected by dying stars and using it to fuel the next generation of star formation. This medium is a complex and dynamic environment, composed of gas, dust, and magnetic fields, all interacting in ways that drive the evolution of galaxies. Within the interstellar medium, regions of high density, such as molecular clouds, become the sites of star formation. The material in these clouds is enriched by the elements produced during the lives and deaths of previous stars, ensuring that each new generation of stars is chemically richer than the last. Galactic recycling, the evolution of the universe. This continuous cycle of stellar birth, evolution, and death is not confined to individual stars. It occurs on a galactic scale, shaping the structure and composition of entire galaxies. Over billions of years, galaxies grow and change as stars form, die, and replenish the interstellar medium. This process is central to the formation of spiral arms, the evolution of galactic cores, and the distribution of elements throughout the galaxy. The concept of galactic chemical evolution describes how successive generations of stars contribute to the increasing abundance of heavy elements in the universe. Early generations of stars, composed almost entirely of hydrogen and helium, produced the first heavier elements through fusion and supernovae. These elements were then incorporated into subsequent generations of stars, leading to the diversity of chemical compositions observed in stars and planets today. The connection to planetary systems and life. The cycle of stellar life is directly linked to the formation of planets and the emergence of life. The elements needed for rocky planets, atmospheres, and biological molecules, carbon, oxygen, nitrogen, silicon, and iron, are all products of stellar processes. Without the contributions of dying stars, planets like Earth would not exist. The timing of this cycle is also critical. Planets form in the protoplanetary disks around young stars, where the material is enriched with elements from earlier generations of stars. These disks provide the raw materials for planets, moons, and other celestial bodies, creating the potential for diverse planetary systems. In some cases, the conditions created by stellar deaths may even contribute to the emergence of life. For example, the shockwaves from supernovae can trigger the collapse of gas clouds, initiating the formation of stars and planetary systems in regions already enriched with the elements needed for life. Observing the cycle, tracing the flow of matter. Modern astronomy allows us to trace the flow of matter through this cosmic cycle in unprecedented detail. Telescopes like the Hubble Space Telescope, the James Webb Space Telescope, and ground-based observatories provide images and spectra of star-forming regions, supernova remnants, and planetary nebulae. These observations reveal how elements are distributed, how stars interact with their environments, and how galaxies evolve over time. The study of cosmic recycling also extends to intergalactic scales. Observations of galactic collisions and mergers show how the interactions between galaxies redistribute stars, gas, and dust, contributing to the enrichment of the universe as a whole. The eternal dance of creation and destruction. The cyclical nature of stellar life is a testament to the interconnectedness of the universe. Stars are born from the ashes of their predecessors, live brilliant lives, and return their material to the cosmos in a process that has been ongoing for billions of years. This cycle ensures the constant renewal of matter, the formation of new stars and planets, and the gradual enrichment of the universe with the elements needed for complexity and life. The role of stars in cosmic timekeeping. In the vast expanse of the universe, where billions of years unfold like pages in a cosmic book, stars serve as some of the most reliable markers of time. Their predictable life cycles, from formation to death, provide astronomers with a natural chronometer to measure the ages of galaxies, star clusters, and even the universe itself. But how do stars reveal the passage of cosmic time? What techniques allow us to decode their lifespans? And why is this understanding so critical to unraveling the history of the cosmos? Stellar evolution as a cosmic clock. The life cycle of a star is determined primarily by its mass. Massive stars live fast and die young, burning through their nuclear fuel in a few million years, while smaller stars like red dwarfs burn slowly and can persist for tens to hundreds of billions of years. This relationship between mass and lifespan provides a natural framework for understanding stellar evolution and estimating the ages of stars. The predictable stages of a star's life. Main sequence, red giant, white dwarf, or supernova, act as milestones that can be compared to theoretical models of stellar behavior. By observing a star's temperature, luminosity, and chemical composition, astronomers can determine its position in its life cycle and estimate how long it has been shining. Measuring ages in star clusters. Star clusters, groups of stars that formed from the same molecular cloud, are particularly valuable for cosmic timekeeping. Because the stars in a cluster share a common origin, their ages can be estimated by studying their collective properties. The main sequence turnoff. One of the most important tools for determining the age of a star cluster is the main sequence turnoff point on the Hertzsprung-Russell (HR) diagram. As stars age and exhaust their hydrogen fuel, they leave the main sequence and evolve into red giants. The location of the turn-off point, where stars are transitioning off the main sequence, indicates the cluster's age. Younger clusters have turn-off points at the hotter, more massive end of the sequence, while older clusters show turn-off points at cooler, less massive stars. Globular clusters, ancient timekeepers. Globular clusters, dense collections of hundreds of thousands of stars, are some of the oldest structures in the universe. By analyzing their main sequence turn-off points, astronomers have determined that many globular clusters are over 12 billion years old, providing crucial insights into the early history of the Milky Way and the formation of galaxies. Variable stars, the pulsing hands of the cosmic clock. Certain types of stars, known as variable stars, change in brightness over time due to intrinsic or extrinsic factors. These variations make them invaluable for measuring distances and time scales in the universe. Cepheid variables. Cepheid variable stars, which pulsate with regular periods, are among the most important tools for cosmic distance measurement. Their pulsation periods are directly related to their luminosities, a relationship known as the period-luminosity relation. By comparing the observed brightness of a Cepheid to its intrinsic luminosity, astronomers can calculate its distance and, in turn, estimate the age of the region in which it resides. RR Lyrae stars. RR Lyrae stars, like Cepheids, are pulsating variables, but they are older and less massive. Found primarily in globular clusters, RR Lyrae stars serve as standard candles for measuring distances within the Milky Way. Their presence in ancient clusters also makes them valuable for studying the early stages of galactic evolution. White dwarfs, cooling clocks of the cosmos. White dwarfs, the remnants of low to medium-mass stars, provide another method for cosmic timekeeping. After shedding their outer layers to form planetary nebulae, white dwarfs cool steadily over billions of years. By measuring their temperatures and comparing them to models of white dwarf cooling, astronomers can estimate their ages. White dwarf cooling has been used to determine the ages of star clusters and even the Milky Way's thin and thick disks. These measurements confirm that the oldest stars in our galaxy formed more than 13 billion years ago, shortly after the Big Bang. Nucleocosmochronology, dating the universe with elements. Beyond individual stars and clusters, the chemical elements produced in stars offer clues to the age of the universe. Nucleocosmochronology is the study of radioactive isotopes, such as uranium-238 and thorium-232, to estimate the time since these elements were created in supernovae. By comparing the ratios of radioactive isotopes to their stable decay products in stellar spectra, astronomers can estimate the ages of the stars containing these elements. This method has provided independent age estimates for the oldest stars in the Milky Way, supporting the timeline established by globular cluster studies and white dwarf cooling. The Hubble constant and cosmic expansion. The age of the universe itself is closely tied to the rate of cosmic expansion described by the Hubble constant. By combining observations of Cepheid variables, type Ia supernovae, and the cosmic microwave background radiation, astronomers have estimated the age of the universe to be approximately 13.8 billion years. Stars play a central role in this calculation. Cepheid variables and supernovae serve as standard candles for measuring distances to galaxies, which are essential for determining the expansion rate. The ages of the oldest stars and clusters provide additional constraints, ensuring consistency between different methods of measuring cosmic time. Timekeeping across the universe. Stars not only help us measure the passage of cosmic time, but also offer glimpses into the processes that shape the universe on all scales. Galactic evolution. By studying the ages of stars in different regions of a galaxy, astronomers can trace its formation history and understand the dynamics of star formation and mergers. Stellar populations. The chemical compositions and ages of stars reveal the history of element production and the role of different generations of stars in enriching the interstellar medium. Planetary systems. The ages of stars hosting exoplanets provide insights into the timing and processes of planet formation, helping to identify systems that might support life. Stars as universal timekeepers. The ability of stars to act as cosmic clocks stems from their intrinsic properties and predictable behaviors. From the rapid evolution of massive stars to the slow cooling of white dwarfs, each phase of a star's life contributes a unique piece to the puzzle of cosmic time. By combining observations across different stellar populations, astronomers can reconstruct the history of galaxies, trace the evolution of elements, and estimate the age of the universe itself. The eternal legacy of stars. As we gaze at the stars, we are not just seeing light from distant suns. We are looking back in time, witnessing the echoes of events that occurred billions of years ago. Stars are the universe's archivists, preserving the story of creation in their life cycles, compositions, and remnants. They remind us that time is woven into the fabric of the cosmos, measured in the light and lives of the stars. The ultimate fate of stars and the universe. As we trace the life cycles of stars, from their fiery births to their transformative deaths, it becomes clear that stars are the engines of the cosmos. Yet, like all things, stars are finite. They live out their luminous lives, transforming matter and energy, before fading into remnants that leave lasting imprints on the universe. But what lies beyond these individual stories? What is the ultimate fate of stars? And how does their destiny intertwine with the far future of the universe itself? To answer these questions, we must project far beyond human timescales, envisioning a universe where stars are no longer born and light itself grows scarce. The final stages of stellar remnants. After stars exhaust their nuclear fuel, they leave behind remnants that persist for billions or even trillions of years. Each type of remnant has a unique trajectory, contributing to the slow evolution of the universe. White dwarfs, cooling to darkness. Low to medium mass stars like the Sun end their lives as white dwarfs. Dense, Earth-sized cores composed mainly of carbon and oxygen. These remnants no longer undergo fusion and instead radiate away their residual heat over billions of years. Eventually, they cool to become black dwarfs, inert objects that no longer emit light or heat. The cooling process is extraordinarily slow, and the universe is not yet old enough for any white dwarfs to have reached this final stage. In the far future, however, black dwarfs will dominate the cosmic landscape, marking the silent remnants of a bygone era of stellar activity. Neutron stars, the quiet titans. Neutron stars, formed from the collapsed cores of massive stars, persist far longer than their progenitors. Though they no longer produce energy, their extreme density and strong magnetic fields make them fascinating objects of study. Over time, neutron stars may lose energy through the emission of electromagnetic radiation or gravitational interactions, gradually fading from detectable view. Black holes, eternal guardians of mass. The most massive stellar remnants, black holes, play a unique role in the universe's long-term evolution. Once formed, black holes grow by accreting nearby matter and merging with other black holes. Over eons, they become the dominant structures in the universe, concentrating mass into regions of intense gravity. Though black holes are often thought to be eternal, even they are not immune to the passage of time. According to Stephen Hawking's theoretical work, black holes slowly lose mass through a process called Hawking radiation. Over unimaginably long time scales, trillions of times the current age of the universe, black holes will evaporate completely, leaving behind a universe devoid of massive structures. The degenerate era, a universe without stars. As stars exhaust their nuclear fuel and no new stars form, the universe will enter the degenerate era, a period dominated by stellar remnants and substellar objects like brown dwarfs. During this era, stellar remnants such as white dwarfs, neutron stars, and black holes will outnumber active stars. Brown dwarfs and rogue planets, objects that never ignited fusion, will drift through the cold, dark voids of space. The interstellar medium, once vibrant with gas and dust, will be depleted, consumed by star formation and accretion over billions of years. The universe will become a quieter place, with little to illuminate the darkness. Gravitational interactions will continue to shape the trajectories of celestial objects, but the creation of light and heat will largely cease. The role of black holes in the far future. In the absence of active stars, black holes will dominate the cosmic landscape. These massive objects, ranging from stellar mass black holes to supermassive ones at the centers of galaxies, will continue to shape their environments through their immense gravitational pull. Over time, galaxies will disintegrate as gravitational interactions fling stars and remnants into intergalactic space. Black holes, however, will remain, anchoring clusters of matter and slowly consuming any material that strays too close. In the far future, even these interactions will dwindle. Black holes will eventually evaporate through Hawking radiation, releasing their energy in the form of faint thermal emissions. This process, though incredibly slow, will mark the final stages of the degenerate era. The black hole era, a universe of fading echoes. After black holes evaporate, the universe will enter the black hole era, a period characterized by near-total darkness. The only remaining sources of energy will be the faint emissions from subatomic processes and the decay of unstable particles. During this era, the last remnants of structure will fade as matter disperses. Any surviving particles will interact less frequently as the universe expands, becoming increasingly isolated. The universe will approach a state of maximum entropy, where energy is evenly distributed and no significant processes occur. This is known as the heat death of the universe, a state of profound stillness and equilibrium. The far future, speculative scenarios. While the heat death of the universe represents the most widely accepted view of the future, alternative scenarios exist based on different interpretations of cosmological principles. 1. Big freeze. The universe continues expanding indefinitely, cooling to near absolute zero as galaxies, stars, and remnants drift apart. 2. Big rip. If dark energy accelerates the universe's expansion, it could eventually tear apart galaxies, stars, and even atomic particles. 3. Big crunch. If the universe's expansion reverses due to gravitational forces, it could collapse into a singularity, potentially leading to a new Big Bang. 4. Cyclic universe. The universe undergoes infinite cycles of expansion and contraction, with each big crunch giving rise to a new Big Bang. These scenarios highlight the uncertainty in predicting the ultimate fate of the cosmos, as they depend on factors like the nature of dark energy and the universe's total mass. The legacy of stars. Even as the universe grows cold and dark, the legacy of stars endures. The elements forged in their cores, scattered through supernovae and stellar winds, form the foundation for planets, life, and the structures we observe today. The light from distant stars, traveling across billions of years, serves as a window into the past, preserving the history of the cosmos. The remnants of stars, white dwarfs, neutron stars, and black holes, will persist as silent witnesses to the universe's evolution, embodying the stories of the stars that once illuminated the cosmos. Reflections on the cosmic cycle. The ultimate fate of stars and the universe reminds us of the transient, yet interconnected nature of existence. Stars are born, live, and die, contributing to a larger cycle of creation and transformation that transcends individual lifespans. Even as the universe approaches its distant destiny, the echoes of this cycle remain, a testament to the dynamic processes that shaped the cosmos. Summarizing the interwoven stories of stars and the cosmos. From the first flickers of starlight in the early universe to the silent remnants that will linger in the cosmos's distant future, the story of stars is one of transformation, interconnection, and profound influence. Stars are not merely luminous points in the night sky. They are the architects of galaxies, the forgers of elements, and the keepers of cosmic time. Their lives and deaths are intertwined with the universe's evolution, shaping its structure, chemistry, and destiny. The birth of stars. From chaos to light. Stars emerge from the dense, shadowy regions of molecular clouds, where gravity pulls gas and dust into compact cores. These protostars ignite nuclear fusion in their hearts, transforming simple hydrogen into helium and radiating light that illuminates the universe. This moment, the birth of a star, is a triumph of balance, a delicate interplay of gravity and pressure that sustains the star for millions or billions of years. Each star's birth carries the imprint of its surroundings. The elements present in the molecular cloud, enriched by previous generations of stars, dictate the star's composition and potential to host planetary systems. In this way, the formation of each star is both a continuation of cosmic history and a prelude to new stories yet to unfold. The life of stars, luminaries of the universe. As stars settle into the main sequence phase, they become engines of energy and synthesis. Through nuclear fusion, stars produce the light and heat that sustain life on planets like Earth. They also forge the elements that make up the universe's complexity, from carbon and oxygen to the iron in our blood. The diversity of stars, ranging from small, long-lived red dwarfs to massive, short-lived blue giants, ensures a variety of contributions to the universe's evolution. Massive stars enrich their surroundings with heavy elements through stellar winds and eventual supernovae, while smaller stars provide stability and longevity, fostering the conditions for planetary development and the emergence of life. The death of stars, transformative endings. When stars reach the end of their lives, they undergo dramatic transformations that ripple across the cosmos. Low to medium-mass stars shed their outer layers to form planetary nebulae, leaving behind dense white dwarfs that gradually cool over billions of years. Massive stars explode as supernovae, scattering heavy elements into space and leaving behind neutron stars or black holes. Binary systems can experience novae, recurrent explosions that temporarily brighten the stars, or catastrophic events like Type Ia supernovae, which serve as cosmic markers for measuring distances. These deaths are not endings but transformations, enriching the interstellar medium and fueling the birth of new stars and planets. Each death sows the seeds for new beginnings, ensuring the universe's continual renewal. The role of stellar remnants. The remnants of stars, white dwarfs, neutron stars, and black holes serve as time capsules, preserving the history of their progenitors. They also play active roles in shaping their surroundings. White dwarfs reveal the cooling history of the cosmos. Neutron stars provide insights into extreme states of matter, and black holes dominate the dynamics of galaxies, even as they slowly evaporate over trillions of years. Stars as cosmic timekeepers. The predictable stages of stellar evolution allow astronomers to measure cosmic time, reconstructing the history of galaxies, clusters, and the universe itself. The ages of globular clusters, the cooling of white dwarfs, and the pulsations of variable stars like Cepheids provide critical clues to the timeline of cosmic events, from the formation of the Milky Way to the age of the universe. The future of stars and the universe. In the far future, as the universe transitions into the degenerate era, stars will fade into remnants, and the cosmos will grow darker. The black dwarfs, neutron stars, and black holes left behind will persist as silent witnesses to the universe's past, gradually dispersing their energy and matter into the void. Yet even in this distant future, the legacy of stars endures. The elements they forged will remain, woven into the fabric of the universe, a testament to their transformative power. The legacy of stars, builders of complexity. Stars are more than luminous objects. They are the builders of complexity in the cosmos. Through their fusion processes and explosive deaths, they create the elements that form planets, atmospheres, and life itself. The carbon in our cells, the oxygen we breathe, and the iron in our blood were all born in stars, connecting us to the vast history of the universe. Stars also inspire. Their light has guided explorers, their constellations have told stories, and their mysteries have driven humanity to probe the limits of knowledge. They remind us of our place in the cosmos, as being shaped by the universe's creative processes. The interwoven story of stars and the cosmos. The story of stars is the story of the universe, a tale of creation, transformation, and renewal. It is a cycle of birth and death, of light and shadow, of simplicity evolving into complexity. Stars connect the smallest particles to the largest structures, weaving together the tapestry of existence. As we look to the future, the study of stars continues to unveil the secrets of the cosmos. From the first stars that illuminated the early universe to the faint whispers of light from ancient remnants, stars guide us in our quest to understand the vast and beautiful universe we call home. Stars and the formation of galaxies. Stars are the building blocks of galaxies, the vast collections of billions of stars bound together by gravity. Early in the universe, the first stars formed from pristine clouds of hydrogen and helium, illuminating the darkness of the cosmic dark ages. These stars, known as population 3 stars, were incredibly massive and short-lived, ending their lives in spectacular supernovae that enriched their surroundings with the first heavy elements. As galaxies evolved, successive generations of stars, population 2 and population 1, contributed to the formation of diverse galactic structures, from the spiral arms of the Milky Way to the dense cores of elliptical galaxies. The interplay between star formation, supernova feedback, and black holes shaped the morphology and evolution of galaxies, creating the vast cosmic tapestry we observe today. Stars as cosmic element factories. One of the most remarkable contributions of stars is their role in the creation of the periodic table's elements. The Big Bang produced only the lightest elements: hydrogen, helium, and trace amounts of lithium. Everything else was forged in stars through nuclear fusion and the violent processes of stellar death. In stellar cores, elements up to iron are created through fusion, releasing the energy that powers the stars. In supernova explosions, elements heavier than iron, such as gold and uranium, are synthesized through the R process, rapid neutron capture. In neutron star mergers, even rarer elements like platinum are formed in immense quantities, enriching the universe with materials critical for complex chemistry and life. Without stars, the universe would be a simpler, more barren place, devoid of the complexity needed for planets, atmospheres, and living organisms. Stars and their role in timekeeping. As natural timekeepers, stars allow astronomers to chart the passage of cosmic time. Their predictable life cycles serve as benchmarks for understanding the age and history of the universe. For example, globular clusters, with their ancient populations of stars, reveal the early history of galaxies. Cepheid variables help map the expansion of the universe and confirm distances to far-off galaxies. White dwarfs, with their slow cooling rates, act as time markers for star formation events. The data provided by stars, combined with cosmological studies, has allowed scientists to estimate the universe's age at approximately 13.8 billion years, a timeline that reveals the interconnectedness of all cosmic phenomena. The emotional and philosophical impact of stars. Stars are not just scientific phenomena. They are deeply woven into human culture and thought. For millennia, they have inspired myths, guided travelers, and fueled our curiosity about the cosmos. From the constellations mapped by ancient civilizations to the modern pursuit of astrophysics, stars have always been a source of wonder. When we look at the night sky, we are gazing at light that has traveled for thousands, even millions of years, a connection to a distant past. This perspective reminds us of our place in the universe, as both observers and participants in its ongoing story. The future of star research. Despite our deep understanding, there is still so much to learn about stars. Future advancements in technology, such as the James Webb Space Telescope and next-generation observatories, promise to unlock new mysteries. The first stars. We are close to detecting the light from the universe's earliest stars, which formed just a few 100 million years after the Big Bang. Exoplanetary systems. Stars hold the keys to understanding the potential for life beyond Earth, as their properties influence the formation and habitability of planets. Stellar remnants. Continued study of neutron stars, pulsars, and black holes will reveal more about the extreme states of matter and the behavior of space-time. Stars remain at the forefront of exploration, serving as beacons that guide us deeper into the universe's secrets. Closing thoughts. Stars are the lifeblood of the cosmos, linking the smallest particles to the largest galactic structures. Their light illuminates not just the universe, but our understanding of existence itself. As science advances, stars will continue to inspire, teach, and challenge us, ensuring that the pursuit of knowledge burns as brightly as they do. Stars and their connection to exoplanets. One of the most exciting areas of modern astronomy is the study of exoplanets, planets that orbit stars beyond our solar system. Stars are the anchors for these planetary systems, and their properties play a critical role in determining the types of planets that form and their potential habitability. Types of exoplanetary systems. Stars with varying masses and compositions host a wide range of planetary systems. Some, like stars, G-type stars, are ideal for hosting Earth-like planets in their habitable zones, where liquid water can exist. Red dwarfs, the most common type of star in the universe, often have close-orbiting planets due to their smaller size and cooler temperatures. Many of these planets lie within the star's habitable zone, but they are subject to intense stellar flares that could strip away atmospheres. Massive stars, like O and B types, rarely host long-lived planetary systems because their short lifespans prevent planets from fully forming or developing stable climates. The habitable zone. The habitable zone around a star is the region where conditions might allow liquid water to exist, a key factor for life as we know it. The size and location of this zone depend on the star's luminosity and temperature. Red dwarfs, with their cool temperatures, have habitable zones very close to the star, while hotter stars push these zones farther out. Exoplanet detection and stellar influence. Techniques like the transit method and radial velocity method rely heavily on observing stars. The transit method detects the slight dimming of a star's light as a planet passes in front of it. The radial velocity method measures the gravitational wobble of a star caused by an orbiting planet. Both techniques highlight how the behavior of stars provides clues to the existence and characteristics of their planetary companions. Stars as laboratories for understanding physics. Stars are not only celestial bodies but also natural laboratories that allow scientists to study physics under extreme conditions that cannot be replicated on Earth. From their dense cores to their explosive depths, stars test the limits of our understanding. Stellar cores, fusion, and matter. The immense pressures and temperatures inside stars enable nuclear fusion, where lighter elements combine to form heavier ones. This process powers stars and demonstrates the fundamental forces of nature: gravity, electromagnetism, and the strong nuclear force. Magnetic fields and stellar winds. Stars like our Sun generate powerful magnetic fields that shape their surfaces and environments. These magnetic fields drive phenomena like sunspots, flares, and coronal mass ejections, which influence surrounding planets and interstellar space. Understanding these processes helps us predict space weather and its effects on Earth. Supernovae and neutron stars. The violent deaths of massive stars create extreme environments where matter behaves in extraordinary ways. In supernovae, temperatures can exceed billions of degrees, producing shockwaves that synthesize heavy elements. Neutron stars, remnants of these explosions, have densities so high that a sugar cube-sized piece of neutron star material would weigh billions of tons. Black holes and space-time. The most enigmatic remnants of stellar evolution, black holes, challenge our understanding of gravity and space-time. Observing the behavior of matter near black holes provides insights into relativistic physics, including phenomena like gravitational lensing and time dilation. The first stars, cosmic pioneers. The first stars, known as population 3 stars, formed about 200 million years after the Big Bang. These stars were massive, short-lived, and composed almost entirely of hydrogen and helium, as heavier elements had not yet been created. Their formation and death. Without the cooling effects of heavier elements, these stars could only form in the densest regions of primordial gas clouds. Their immense masses led to rapid nuclear fusion, burning through their fuel in just a few million years. Their explosive deaths seeded the universe with the first heavy elements, paving the way for later generations of stars and planets. Searching for population 3 stars. Although these stars have long since died, their existence is inferred through the chemical compositions of ancient stars and the structure of early galaxies. Observatories like the James Webb Space Telescope are poised to detect the faint light from these early stars, providing a glimpse into the universe's first moments of light and structure. The dynamic role of dark matter in star formation. Stars do not exist in isolation. They are shaped by the dark matter halos that surround galaxies. Dark matter, an invisible and mysterious form of matter, provides the gravitational framework within which galaxies and stars form. Dark matter and star formation. The presence of dark matter influences the collapse of gas clouds, guiding the formation of stars and star clusters. Without dark matter's gravitational pull, the process of star formation would be far less efficient, and galaxies as we know them might not exist. Galactic evolution. The interaction between stars and dark matter determines the structure and evolution of galaxies. Stars trace the gravitational patterns created by dark matter, revealing its distribution and behavior. Stars as narrators of cosmic history. Stars carry within them the history of the universe. Old stars preserve the chemical fingerprints of the early cosmos, showing what the universe was like when they formed. Young stars reflect the enriched conditions of more recent star formation, influenced by generations of stellar death and rebirth. Variable stars like Cepheids and RR Lyrae serve as distance markers, allowing astronomers to map the cosmos and trace the expansion of the universe. By studying stars, we reconstruct the narrative of cosmic evolution, from the first flickers of light to the modern universe's complex structure. Looking forward, the future of stellar research. As technology advances, so does our ability to study stars. The next generation of telescopes, such as the Extremely Large Telescope, YELT, and space missions like the Roman Space Telescope, promise to revolutionize our understanding of stars and their roles in the cosmos. Key questions drive the future of stellar research. How do stars influence the habitability of planets? What processes govern the deaths of the most massive stars? How did the earliest stars shape the structure of the universe? What can stellar remnants reveal about the nature of matter and energy? The eternal legacy of stars. The life and death of stars form the backbone of the universe's story. They are the forgers of elements, the architects of galaxies, and the custodians of time. From their fiery births in dense clouds to their quiet deaths as remnants, stars illuminate the cosmos in every sense. Even as the universe moves toward its distant fate, the legacy of stars will persist. Their light, though fleeting, connects us to the vastness of the cosmos, reminding us that we are part of an ever-evolving universe, one shaped, in no small part, by the lives of stars. Stars and the cycles of creation. Stars are not solitary players in the cosmic drama. They participate in intricate cycles of creation, destruction, and renewal. These cycles are essential for the ongoing evolution of galaxies and the formation of planets, enriching the universe with the elements and energy necessary for life. Stellar feedback loops. Stars profoundly influence their environments through feedback processes. Stellar winds. High energy outflows from young, massive stars can sculpt the surrounding interstellar medium, compressing gas clouds and triggering new star formation. At the same time, they can also disperse gas, halting further star formation in their immediate vicinity. Supernova explosions. The shock waves from supernovae compress gas clouds, providing the initial push for gravitational collapse that leads to new star formation. This process perpetuates the cycle of stellar birth and death, ensuring the continuous rejuvenation of the galaxy. Chemical enrichment. As stars live and die, they recycle matter into the interstellar medium. Low-mass stars, through planetary nebulae, return lighter elements like carbon and nitrogen. Massive stars, through supernovae, distribute heavier elements like iron and nickel. Neutron star mergers and kilonovae forge the rarest and heaviest elements, including gold and platinum. This gradual enrichment of the universe's material reservoir allows successive generations of stars and planets to form with increasingly complex compositions. The role of stars in galactic ecosystems. Stars are the keystones of galactic ecosystems, driving processes that define the evolution of entire galaxies. Starburst galaxies. In some galaxies, intense bursts of star formation occur, producing thousands of new stars in a short time. These starburst galaxies are often triggered by interactions or mergers with other galaxies. The newly formed stars rapidly consume available gas and dust, leading to a feedback cycle that either sustains or quenches further star formation. Quenching and galaxy evolution. As galaxies age, their star formation rates decline, often due to the influence of supermassive black holes at their centers. These black holes, through processes like accretion and jet formation, can heat or expel gas from the galaxy, effectively quenching star formation. This interplay between stars, gas, and black holes shapes the life cycle of galaxies, from youthful star-forming spirals to quiescent elliptical systems. Stars and the emergence of life. The connection between stars and life is deep and multifaceted. Stars provide the energy, elements, and stability necessary for the development of habitable environments. Energy from stars. Stars are the primary energy source for planets. Their light drives the chemical reactions that sustain life, from photosynthesis on Earth to potential subsurface ecosystems on exoplanets orbiting dim red dwarfs. Stable environments. A star's stability is critical for habitability. Stars like the Sun provide a relatively steady energy output, creating conditions that allow life to evolve over billions of years. In contrast, stars with highly variable outputs or frequent flares can strip planetary atmospheres or disrupt biological processes. The building blocks of life. The elements necessary for life, carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur, are all products of stellar processes. The dust and gas ejected by dying stars become part of the molecular clouds that form new planetary systems, embedding the ingredients for life into nascent planets. The cosmic importance of binary and multi-star systems. While many stars exist in isolation, a significant fraction are part of binary or multi-star systems. These configurations add complexity to the interactions between stars and their planets. Planet formation in binary systems. Planets and binary star systems experience gravitational influences from both stars, which can either stabilize or destabilize their orbits. Some binary systems produce stable, wide orbits where planets can thrive, while others create chaotic conditions that make planet formation challenging. Stellar interactions. In close binary systems, mass transfer between stars can lead to phenomena like accretion disks. Material from one star forms a disk around the other, creating bright emissions and sometimes leading to novae or X-ray binaries. Type Ia supernovae. White dwarfs and binary systems can accrete enough mass to trigger runaway fusion, producing these powerful explosions. The dynamics of binary systems enrich the diversity of stellar phenomena and deepen our understanding of stellar evolution. The enduring mysteries of stars. Despite centuries of study, stars continue to pose profound questions. The first stars. How exactly did population 3 stars form in the pristine early universe? And what were their properties? Star formation efficiency. Why do some molecular clouds produce abundant stars while others remain relatively inert? Stellar remnants. What can neutron stars and black holes reveal about the behavior of matter under extreme conditions? Magnetic fields. How do stars generate and sustain their magnetic fields? And what role do these fields play in stellar evolution and habitability? Stars and the universe's future. In the distant future, as the universe expands and cools, the role of stars will diminish. Yet, their legacy will persist. White dwarfs will cool into black dwarfs, becoming relics of their former brilliance. Neutron stars and black holes will continue to influence their surroundings for trillions of years, shaping the remnants of galaxies. The elements forged in stars will remain embedded in the universe, potentially seeding life in other corners of the cosmos. Even as the stars fade, their contributions will endure, woven into the fabric of the universe's ultimate destiny. Stars are the architects of the cosmos, the alchemists of the elements, and the storytellers of time. They shape the galaxies, enrich the universe with the ingredients of life, and guide us in our quest to understand the cosmos. As humanity continues to explore the stars, we deepen our connection to the universe. In their light, we find not just answers, but inspiration, an eternal reminder that we, too, are part of the grand story of the cosmos. If you like the video, don't forget to subscribe to the channel. This helps my work a lot and shows me that you are interested in me continuing to produce more videos.